So, here's something worth thinking about as you settle in tonight. Right now, in the mattress underneath you, in the blanket over you, in the air moving quietly in and out of your lungs, there are atoms that were forged inside stars that died before the sun was born. The calcium in your bones, the iron in your blood, the oxygen you just breathed in. All of it came from somewhere very old, very far away, and very violent. And all of it fits, quietly and exactly, into one chart that hangs on classroom walls around the world. Tonight, we're going to go through the whole story of that chart, the periodic table, from the very beginning, the history, the core ideas, all the way through to how it works today. By the end, you'll understand not just what the periodic table is, but why it's shaped the way it is, why it works as a kind of map, and why scientists still argue about where it ends. If you fall asleep somewhere along the way, that's perfectly fine. That's the point. The ideas will still be here if you want to come back to them. Nothing about tonight requires you to stay awake for all of it. Let your body do what it wants to do. The explanation continues either way. To understand the periodic table, we have to go back a very long way, long before anyone had beakers or lab coats, or even the word chemistry. We have to go back to ancient Greece, to a thinker named Empedocles, who lived on the island of Sicily around 2,400 years ago. Empedocles looked at the world around him, the mountains, the rivers, the fires, the wind moving through the trees, and he proposed something simple. He said that everything in existence was made from just 4 basic substances: earth, water, air, and fire. He called these the 4 roots, though later thinkers would call them elements, and the name stuck for centuries. According to Empedocles, nothing new was ever truly created, and nothing was ever truly destroyed. Things simply changed because these 4 roots combined and separated in different ratios, pulled together by a force he called love, and pulled apart by a force he called strife. A tree, in his thinking, was earth and water combining under sunlight, which was a kind of fire. A cloud was water lifted by air. It was a beautiful idea, poetic even, and it felt intuitively correct to people looking at the world with only their eyes and their reasoning to guide them. Aristotle came a century later and expanded on this idea rather than replacing it. He kept the 4 elements but added qualities to each one. Earth was cold and dry, water was cold and wet, air was hot and wet, fire was hot and dry. He also proposed a 5th element, a perfect, unchanging substance he called aether, which he believed made up the stars and the heavens, separate from the imperfect, changing world below. Aristotle's authority was so significant in the ancient and medieval world that his 4-element theory, with its qualities and its aether, became the accepted explanation for the physical world for almost 2,000 years. Think about that for a moment. An idea proposed by people without microscopes, without any way to look closer than the naked eye could see, held firm as the leading explanation of matter for 2 millennia. It shaped medicine, it shaped philosophy, it shaped how ordinary people understood their bodies and the natural world around them, because ancient medicine borrowed the 4 elements directly, turning them into the 4 humors: blood, phlegm, black bile, and yellow bile, which doctors believed governed health and illness for centuries afterward. But there was another thread of thinking happening in ancient Greece at roughly the same time, one that would turn out, eventually, to be much closer to the truth, even though almost nobody believed it at the time. A philosopher named Democritus, along with his teacher Leucippus, proposed something radically different. They said that if you took a piece of matter and cut it in half, and then cut that half in half again, and kept going, eventually you would reach a point where you could not cut any further. You would reach a tiny, indivisible particle. They called this particle atomos, meaning uncuttable, which is where our word atom comes from today. Democritus believed these atoms were infinite in number, came in different shapes and sizes, and moved through empty space, colliding and combining to form everything we see. Fire atoms were small and sharp, which was why fire could burn you. Water atoms were smooth and round, which was why water could flow. It was a mechanical, almost mathematical way of imagining the world, stripped of the poetic forces of love and strife that Empedocles had proposed. Here is the strange part. Democritus's idea was closer to what we now know to be true, and yet it lost the argument for nearly 2,000 years. Aristotle rejected atomism outright, partly on philosophical grounds, arguing that a true vacuum, the empty space atoms would need to move through, was logically impossible. Because Aristotle's ideas carried so much weight, atomism became a minority position, kept alive mostly by a few philosophers and poets, most famously the Roman poet Lucretius, who wrote a long poem called On the Nature of Things, that preserved atomist ideas for later centuries to rediscover. But for the vast majority of the ancient and medieval world, matter was earth, water, air, and fire, and that was simply how things were. It's worth knowing, too, that the four-element idea, or something close to it, was not unique to Greece. In ancient China, a parallel system developed independently, called Wu Xing, usually translated as the 5 phases or 5 elements, consisting of wood, fire, earth, metal, and water. Unlike the Greek system, Wu Xing was never really meant as a literal claim about the physical composition of matter in the way Empedocles intended his 4 roots. It was more a way of describing cycles of change and relationship, wood feeding fire, fire creating ash which becomes earth, earth bearing metal, metal collecting water, water nourishing wood, around and around. It shaped Chinese medicine, astrology, and philosophy for over 2,000 years, running on a track almost entirely separate from the European tradition, arriving at a structurally similar idea, a small handful of basic substances explaining the world, through a completely different cultural path. In ancient India, a similar 5-element system existed as well, called Panchamahabhuta, consisting of earth, water, fire, air, and a 5th element, Akasha, usually translated as space or ether, which appeared independently in Indian philosophy centuries before Aristotle proposed his own 5th element in Greece. None of these systems, Greek, Chinese, or Indian, arrived at anything resembling the modern periodic table, but their persistence across so many independent cultures tells us something. Human beings, looking at the world with only their senses to guide them, kept arriving at the same intuition that the enormous variety of matter around them had to be reducible to some small number of basic ingredients. The intuition was correct. It would just take a very long time, and a much stranger answer than fire, water, earth, and air, to find out what those ingredients actually were. While Europe held on to the 4-element theory, a different and in many ways more practical tradition was developing elsewhere, in the workshops of alchemists across the Islamic world, China, and later medieval Europe. Alchemy is often remembered today as a kind of pseudoscience obsessed with turning lead into gold, and there is truth in that, but alchemy was also, quietly and gradually, the beginning of real experimental chemistry. One of the most important alchemists was a scholar named Jabir ibn Hayyan, who lived in the 8th century in what is now Iraq. Jabir is sometimes called the father of chemistry, and for good reason. He developed and refined laboratory techniques that chemists still use today in some form, including distillation, crystallization, and evaporation. He also proposed that metals were formed from combinations of 2 principles: sulfur, which represented the quality of combustibility, and mercury, which represented the quality of being liquid and shiny. This was still a long way from anything resembling the modern periodic table, but it represented something important. Jabir and the alchemists who followed him were not just philosophizing about matter in the abstract. They were mixing substances, heating them, distilling them, and carefully recording what happened. They were building, slowly and without realizing it, the habits of mind that real chemistry would eventually need. Alchemy spread from the Islamic world into medieval Europe, where it took on a somewhat different character, more focused on the dream of transmutation, changing common metals into gold, and on the search for what alchemists called the philosopher's stone, a substance believed capable of not only creating gold, but also granting immortality. Most of this work, viewed from today, looks like a mixture of genuine chemical experimentation and mystical, almost religious belief. Alchemists worked in secrecy, often using coded symbols and deliberately obscure language to protect their supposed discoveries from rivals. And yet, buried inside centuries of secretive, sometimes fraudulent, sometimes sincere experimentation, real discoveries were made. Alchemists isolated substances like sulfuric acid, nitric acid, and various salts. They discovered how to produce phosphorus. They built better furnaces, better glassware, better methods of purification. All of this groundwork, unglamorous and slow, was quietly preparing the tools that real chemistry would eventually need to use. China had its own long alchemical tradition too, running for centuries in parallel with the one developing in the Islamic world and Europe, though pointed toward a somewhat different goal. Chinese alchemists, going back at least to the 2nd century before the Common Era, focused heavily on the search for an elixir of immortality rather than the pursuit of gold, mixing minerals like mercury, sulfur, and various arsenic compounds in the hope of producing a substance that could extend life indefinitely. There's a genuinely sobering irony buried in this history. Several Chinese emperors, seeking to live forever, drank elixirs prepared by court alchemists containing mercury, a substance we now know to be a slow, cumulative poison, and some historians believe this practice may have shortened rather than lengthened the lives of at least a few of the rulers who trusted it most. And yet, threaded through this same tradition, real chemical knowledge accumulated. Chinese alchemists are credited with some of the earliest documented experiments involving what would later become gunpowder, discovered, according to some historical accounts, somewhat by accident, while alchemists were mixing sulfur, charcoal, and saltpeter in search of that same elusive elixir of immortality, and instead produced something that burned violently instead of extending anyone's life at all. Back in Europe, one especially colorful figure deserves mention, a Swiss physician and alchemist who lived in the early 1500s and went by the adopted name Paracelsus. Paracelsus rejected much of the old Greek medical tradition built on the four humors, and instead argued that chemistry, not ancient philosophy, should be the true foundation of medicine, an idea that was controversial at the time, but that pointed directly toward the modern field of pharmacology. He introduced the use of specific mineral compounds, including compounds of mercury, antimony, and other metals, as deliberate medical treatments, reasoning that the right substance in the right dose could heal, while the same substance in the wrong dose could kill, a principle he summarized with a phrase still quoted by toxicologists today, that the dose makes the poison. Paracelsus was, by most accounts, a difficult and combative personality, reportedly burning the medical textbooks of the ancient physician Galen in public as a show of contempt for what he saw as outdated authority. But underneath the theatrics, he was pushing chemistry and medicine to actually test their claims against real, observable results in real patients, rather than simply repeating what ancient authorities had written centuries earlier, a habit of mind that would become absolutely essential once real experimental chemistry began to take shape a century and a half later. By the time we reached the 1600s, a shift was beginning. A chemist and natural philosopher named Robert Boyle, working in England, published a book in the year 1661 called The Sceptical Chemist. In it, Boyle did something that seems obvious now, but was genuinely radical at the time. He challenged the ancient four-element theory directly. He argued that the four elements of Aristotle were not actually the basic building blocks of matter at all, because nobody had ever actually demonstrated that fire, water, earth, and air could be extracted, pure and unchanged, from other substances. Boyle proposed a new, more careful definition of what an element should be. He said an element should be a substance that cannot be broken down into any simpler substance through chemical means. This was an enormous conceptual leap. It moved the definition of an element away from ancient philosophy and towards something that could actually be tested in a laboratory. If you claim something is an element, Boyle was essentially saying, you need to try to break it apart, and if you cannot, then your claim holds. If you can, it doesn't. This simple shift, testability over authority, is really where modern chemistry begins to take shape. Boyle himself did not manage to identify very many true elements under his new definition, and for a while chemistry continued to be tangled up with an idea that would dominate the field for the next century, an idea called phlogiston theory. Phlogiston theory proposed that flammable materials contained an invisible substance called phlogiston, and that when something burned, it was releasing this phlogiston into the air. A candle burning down, wood turning to ash, metal rusting, all of these were explained as the loss of phlogiston. It was a genuinely useful theory in some ways, because it correctly linked burning, rusting, and breathing together as related processes, even though the actual explanation was backward. Metals, when they rusted, actually gained mass rather than losing it, which was a serious problem for phlogiston theory, one that its supporters struggled for decades to explain away, sometimes proposing that phlogiston had negative weight, an increasingly awkward patch on a theory that was slowly cracking under the weight of careful measurement. The person who finally broke phlogiston theory apart, and who is often credited as the founder of modern chemistry, was a French scientist named Antoine Lavoisier, working in the 1770s and 1780s. Lavoisier's great contribution was not a single discovery so much as a method. He insisted on precise measurement. He weighed everything, before a reaction and after a reaction, using carefully calibrated balances, and he found something phlogiston theory could not explain. When substances burned in a sealed container, the total weight of everything inside the container, including the air, stayed exactly the same. Nothing was created, and nothing was destroyed. Matter was simply being rearranged. This idea, the conservation of mass, became one of the bedrock principles of chemistry. Lavoisier also identified and named oxygen, correctly describing its role in combustion and in breathing, replacing the phlogiston explanation with one that actually matched what the scales were telling him. And in 1789, Lavoisier published a book that included something remarkable for its time, a list of 33 substances he believed to be true chemical elements, based on Boyle's definition, substances that could not be broken down further using the chemistry available at the time. Some of the items on his list were correct: oxygen, hydrogen, nitrogen, and several metals we still recognize as elements today. Some were not. Light and heat were on his list, mistakenly treated as material substances rather than forms of energy. But the list itself was a turning point. For the first time, someone had tried to build a systematic, evidence-based catalog of the basic substances of matter, rather than relying on ancient philosophy or alchemical mysticism. Lavoisier's story has a genuinely sad ending, worth mentioning briefly, because it says something about the era he lived through. He was not only a chemist but also a tax collector for the French crown, a role that made him wealthy but also made him deeply unpopular during the French Revolution. In 1794, at the height of the Revolution's most violent period, Lavoisier was arrested, tried, and executed by guillotine, accused of crimes connected to his tax-collecting work rather than anything related to his scientific research. The mathematician Joseph Louis Lagrange, a contemporary of Lavoisier's, is said to have remarked afterward that it had taken only a moment to cut off that head, and that 100 years might not produce another one like it. Lavoisier was 48 years old, and still, by most accounts, near the height of his scientific productivity when he died. This is where we have to stop and notice something. By the end of the 1700s, chemists finally had a working definition of an element, and they had a growing list of substances that fit that definition. But they had no idea why some elements behaved similarly to each other, why sodium and potassium, for instance, both reacted violently with water in almost identical ways, while other elements seemed to have nothing in common with anything else at all. They had pieces, but no pattern. And that absence of pattern was about to become the central problem driving chemistry forward for the next 100 years. The 1800s opened with a question that Lavoisier's list could not answer. If elements were the basic building blocks of matter, why did some of them behave so much like each other and others behave so differently? Chemists at the start of the century were essentially collectors. They had identified more and more elements, sulfur, phosphorus, various metals, but they had no organizing principle, no reason for the similarities and differences they kept observing in the laboratory. It was a bit like having a room full of unlabeled keys with no idea which doors they opened, or why some keys looked so much alike. The first real step toward an answer came from an English chemist and schoolteacher named John Dalton in the very first years of the 1800s. Dalton picked up the old, mostly abandoned idea of atomism from Democritus, more than 2,000 years after it had first been proposed, and gave it a scientific foundation it had never had before. Dalton proposed that all matter was made of tiny, indivisible particles called atoms, that atoms of a given element were all identical to each other in mass and properties, that atoms of different elements were different from one another, and, crucially, that atoms combined in simple whole number ratios to form compounds. This last point was enormously important because it meant chemistry could become mathematical. If water was always made of the same simple ratio of hydrogen atoms to oxygen atoms, no matter where the water came from, that was a testable, measurable claim, and it turned out to be true. Dalton even attempted to assign relative weights to different atoms, comparing them to hydrogen, which he treated as the lightest and gave a value of 1. His numbers were not entirely accurate because the technology and understanding of the time made precise measurement difficult, but the concept that atoms had specific, comparable weights was exactly the kind of idea chemistry needed. For the first time, elements were not just a list of substances. They were now particles with measurable properties, weight chief among them, that could be compared side by side. Dalton's path to this idea is itself worth knowing, because he did not arrive at atomic theory purely through chemistry. He came to it partly through meteorology of all things. Dalton kept detailed daily weather records for most of his adult life, tens of thousands of observations recorded over more than 50 years. And his interest in gases, in how different gases mix together in the atmosphere without separating out by weight the way you might expect, pushed him to think carefully about what gases were actually made of, at the smallest possible scale. He also studied a peculiar vision problem that ran in his own family, an inability to distinguish certain colors, particularly red and green, and his detailed scientific description of the condition was thorough enough that the disorder was named color blindness, of the Daltonian type for many years afterward, still occasionally called Daltonism in some languages today. It's a small reminder that the people who build the foundations of a field are rarely narrow specialists. Dalton was a weather watcher, a teacher, and a careful observer of his own body, long before any of that curiosity crystallized into atomic theory. Dalton's theory also produced a specific, testable prediction, something chemists call the law of multiple proportions, and it's worth understanding because it's a good example of exactly the kind of evidence that made atomic theory convincing rather than merely elegant. Dalton noticed that when two elements combine to form more than one possible compound, the ratios of one element to the other, across those different compounds, always work out to simple whole numbers. Carbon and oxygen, for instance, can combine in one ratio to form carbon monoxide, and in a different, exactly doubled ratio to form carbon dioxide. This was exactly what you would expect if matter were made of discrete, countable atoms combining in whole number ratios, and it would be very difficult to explain if matter were instead some kind of smooth, infinitely divisible continuous substance, with no natural smallest unit at all. Measurement after measurement confirmed the pattern, and each confirmation made the atomic theory a little harder to dismiss as mere philosophical speculation. Once chemists had the idea of atomic weight, a new project became possible, comparing elements not just by how they behaved, but by how heavy their atoms were. And almost immediately, patterns began to appear. A German chemist named Johann Wolfgang Dobereiner, working in the 18-teens and 1820s, noticed something curious. Certain elements seemed to cluster naturally into groups of three, which he called triads, where the elements shared very similar chemical properties, and where the atomic weight of the middle element was almost exactly the average of the atomic weights of the other two. Calcium, strontium, and barium formed one such triad. Chlorine, bromine, and iodine formed another. Lithium, sodium, and potassium formed a third. This was a genuinely important observation, because it suggested, for the first time, that atomic weight was not just a random number attached to each element, but was somehow connected to chemical behavior. If the weights lined up mathematically and the properties lined up chemically at the same time, that could not simply be a coincidence. But Dobereiner's triads only worked for a small handful of elements. Most known elements did not fit neatly into groups of three, and Dobereiner had no way to explain why the pattern existed at all, only that it did, in these specific cases. Decades passed, and more elements were discovered, and more attempts were made to find the pattern hiding underneath them. In the 1860s, an English chemist named John Newlands tried arranging all the known elements in a single row, ordered strictly by increasing atomic weight from lightest to heaviest. When he did this, he noticed something that reminded him of music. Every eighth element, counting along the row, seemed to share properties with the element 8 places earlier. He called this pattern the law of octaves, borrowing the term directly from musical scales, where a note repeats itself at a higher pitch every 8 notes. It was a striking idea, and it was actually onto something real. But Newlands presented it at a time when many known elements did not fit the pattern cleanly, particularly among the heavier elements, and the musical framing made some of his peers openly skeptical, even mocking, at a meeting of the London Chemical Society, where he was reportedly asked, with some sarcasm, whether he had tried arranging the elements alphabetically instead, to see if that produced any patterns too. Newlands's idea was dismissed at the time and not taken seriously by the wider chemistry community. It would take years before anyone recognized how close he had actually come to something real. The person who is generally credited with the true breakthrough, the one whose work laid the actual foundation of the periodic table we still use today, was a Russian chemist named Dmitri Mendeleev. Mendeleev's early life was not an easy one. He was reportedly the youngest of somewhere between 14 and 17 children, accounts vary, born in Siberia to a family that fell into serious hardship after his father lost his eyesight and his mother's glass factory burned down. His mother, determined that her youngest son receive a proper education, made an enormous personal journey, traveling with him across a significant stretch of the Russian Empire to secure his admission to a teacher training institute in St. Petersburg, and she died shortly after finally succeeding, a sacrifice Mendeleev reportedly carried with him for the rest of his life. He went on to study in Germany, worked as a professor, and developed a reputation as a brilliant but somewhat eccentric and famously disheveled figure, said to cut his own hair and beard only once a year, and known for genuine bursts of temper alongside genuine warmth toward his students. In the year 1869, Mendeleev was working on a chemistry textbook and trying to find a logical, teachable way to organize the 63 elements known at the time. Like Newlands before him, he arranged the elements by atomic weight. But Mendeleev did something braver and more careful than his predecessors. Where an element's properties did not fit the pattern in its expected position, rather than force it to fit or abandon the pattern altogether, Mendeleev did something remarkable. He left a gap. He proposed that the pattern itself was more reliable than the incomplete data chemists had at the time, and that the gaps represented elements that had simply not been discovered yet. This was an extraordinary act of scientific confidence. Mendeleev was not just organizing what was known. He was making predictions about what was still unknown, based purely on the strength of the pattern he had found. Mendeleev went even further. For 3 of these gaps, he predicted, in remarkable detail, the properties the missing elements would have once discovered, based on the properties of the elements around the gap in his table. He called these hypothetical elements by placeholder names, borrowing from Sanskrit eka boron, eka aluminum, and eka silicon, meaning roughly one beyond each of those known elements. He predicted approximate atomic weights, densities, and chemical behaviors for each. And then, remarkably, chemistry began to catch up to him. In 1875, a French chemist named Paul-Émile Lecoq de Boisbaudran discovered a new element through a technique called spectroscopy and named it gallium after France. Its properties matched Mendeleev's predicted Eka aluminum almost exactly. The density, the atomic weight, even the way it melted at a surprisingly low temperature for a metal. A few years later, in 1879, a Swedish chemist discovered scandium, matching Eka boron, and in 1886, a German chemist named Clemens Winkler discovered germanium, matching Eka silicon so closely in weight, density, and chemical behavior that it became one of the most celebrated confirmations in the history of chemistry. Mendeleev had not just organized existing knowledge, he had used that organization to see into the future, correctly describing elements that no human being had ever observed, based purely on the logic of the pattern. It's worth mentioning that Mendeleev was not working entirely alone in this pursuit, even if history remembers his name most clearly. A German chemist named Lothar Meyer was independently developing a strikingly similar table at almost exactly the same time, in the late 1860s, also organizing elements by atomic weight and also noticing the same repeating patterns in their properties. Meyer even published a graph plotting atomic weight against atomic volume that showed the same periodic rise and fall Mendeleev's table captured in tabular form. But Meyer was more cautious than Mendeleev, less willing to commit to bold predictions about undiscovered elements, and his final version of the table, delayed by his own hesitance to publish, appeared after Mendeleev's. Because Mendeleev had been the one willing to state, in print, specific predictions about elements nobody had yet found, and because those predictions then came true in such dramatic fashion, history settled on his name as the discoverer of the periodic law, though Meyer is still remembered today as an important, largely simultaneous co-discoverer, a reminder that major scientific ideas often arrive nearly at once, in more than one mind, once the surrounding evidence has accumulated enough to make the pattern visible to anyone looking closely and carefully enough. It's worth pausing here to really sit with what this meant. Mendeleev's table was not just a filing system for known facts. It behaved like a genuine scientific law, something with real predictive power, the same kind of power that lets astronomers predict where a planet will be years before they look through a telescope to confirm it. When a scientific idea can predict something nobody has seen yet, and then that prediction turns out to be correct, that is one of the strongest signals available that the idea is describing something real about the universe, rather than just a convenient way of sorting information that happens to already exist. Mendeleev's table passed that test, repeatedly, which is why, of everyone who worked on this problem across the 1800s, his name is the one that survived attached to the achievement. Mendeleev's original table was not perfect, and it's worth being honest about that too. Ordering elements strictly by atomic weight caused some genuine problems, because a small number of elements, when placed by weight alone, ended up sitting in the wrong group, next to elements they did not actually resemble chemically. Mendeleev, trusting the chemical pattern over the raw numbers, sometimes swapped pairs of elements out of strict weight order to keep the chemistry consistent, correctly guessing, without being able to prove why, that atomic weight was not quite the true underlying organizing principle after all, just a very good approximation of it. It would take several more decades and an entirely new understanding of what atoms are actually made of before anyone could explain why his instinct to prioritize chemical behavior over raw weight had been the right one. Before we get to that deeper understanding, there's one more gap in Mendeleev's table worth mentioning, because it wasn't a gap he predicted at all, and it exposed a genuine blind spot in the pattern as he understood it. In the 1890s, a British chemist named William Ramsay, working with the physicist Lord Rayleigh, noticed something odd while carefully measuring the density of nitrogen gas extracted from the air. Nitrogen obtained from ordinary air was consistently very slightly heavier than nitrogen produced through purely chemical reactions in the laboratory. The difference was tiny, but Ramsay and Rayleigh trusted their measurements enough to investigate further, and they eventually isolated a completely new gas hiding within ordinary air, one that refused to react with anything at all, no matter what they tried. They named it argon, from a Greek word meaning idle or inactive, a fitting name for an element that seemed to do nothing chemically whatsoever. This was strange, because Mendeleev's table, as it stood, had no place for an entire family of elements that reacted with nothing. Ramsay kept looking, and over the following several years discovered an entire new column's worth of similarly unreactive gases, neon, krypton, and xenon, along with helium, which had actually been detected years earlier in the light spectrum of the sun during a solar eclipse, given its name from the Greek word for the sun itself, but had not yet been found on Earth until Ramsay identified it here too. Rather than breaking Mendeleev's table, this discovery completed it in a way nobody had anticipated, revealing an entirely new group, the noble gases, that needed to be inserted as a brand new column, and which, once placed, made the pattern of the whole table even more convincing, because these new, chemically silent elements slotted perfectly into place, extending the logic of the table into territory nobody had thought to predict. That understanding of what atoms are actually made of did not arrive until the very end of the 1800s and the early years of the 1900s, and it began with the accidental detection of radioactivity, which cracked open the atom in a way nobody had anticipated. Atoms, remember, had been defined by Dalton as indivisible, uncuttable, exactly as their ancient Greek name suggested. But in 1896, a French physicist named Henri Becquerel noticed that certain uranium compounds gave off a mysterious form of energy on their own, without any external source of light or heat. The uranium salts left marks on photographic plates wrapped in dark paper, marks that should not have been there unless some kind of invisible ray was passing through the paper. It was a quiet observation, made almost by chance, but it pointed towards something deeply strange. Atoms, the supposedly solid and permanent particles that made up all matter, could spontaneously emit energy. And not just energy. Over time, as physicists studied this phenomenon more closely, they realized that some atoms could actually transform into entirely different elements as they did so. Marie Curie, working alongside her husband Pierre Curie in Paris, threw herself into studying this phenomenon from the very beginning. It was Curie who coined the term radioactivity to describe what she was seeing. She went on to identify two new radioactive elements herself, polonium, which she named after her native Poland, and radium. The work was punishing in ways that are difficult to fully appreciate now. Curie processed literally tons of a mineral called pitchblende by hand in a poorly ventilated shed with a leaking roof, boiling enormous vats of ore, filtering, crystallizing, grinding, and stirring, over and over again, for years, in order to isolate just a fraction of a gram of pure radium at the end of it all. The physical labor alone would have been exhausting for anyone, but she and her husband did not yet understand the danger of what they were handling. Radium glows faintly on its own, a soft blue-green light visible in the dark, and the Curies reportedly kept samples of it in their bedroom at night, simply because they found the glow beautiful. They had no way of knowing that the radiation quietly damaging their bodies with every passing hour would eventually be understood as one of the most serious hazards in all of chemistry. Marie Curie would eventually become the first person of any gender to win 2 Nobel Prizes in 2 different scientific fields, physics and chemistry, an achievement that remains extraordinarily rare even today, held only by a handful of people in all of history. She died in 1934 from a blood disorder almost certainly caused by decades of radiation exposure. To this day, her personal papers and notebooks are kept in lead-lined boxes in the French National Library, still too radioactive to handle without protection, more than 90 years after her death. The very pages she wrote on, the very notebooks she touched with her bare hands day after day, still carry enough residual radiation to require shielding. It's a sobering reminder, if one were needed, that the forces she helped bring to light were genuinely powerful, forces that do not distinguish between a scientist studying them and a body simply present in the same room. Radioactivity forced physicists to accept something they had never expected. If atoms could spontaneously give off energy and in some cases transform into entirely different elements as they did so, then atoms could not be the simple, solid, indivisible spheres Dalton had imagined. There had to be internal structure. Something inside the atom had to be capable of rearranging itself, capable of coming apart. The atom was not a period at the end of a sentence, a final, irreducible point. It was a tiny world with its own internal architecture, waiting to be mapped. A New Zealand-born physicist named Ernest Rutherford, working in England, ran a now famous experiment in 1911, though the actual hands-on work was carried out by two researchers in his laboratory, Hans Geiger and Ernest Marsden, following Rutherford's direction. They fired a stream of tiny, positively charged particles, called alpha particles, at an extremely thin sheet of gold foil, only a few atoms thick. They watched, using a screen coated in a material that flashed faintly with light wherever a particle struck it, to see where the particles ended up after passing through the foil. Most of the particles passed straight through with barely any deflection at all. This was exactly what the leading atomic model of the time predicted. That model, proposed a few years earlier by the physicist J.J. Thomson, who had identified the electron in 1897, pictured the atom as something like a plum pudding, a diffuse, evenly spread cloud of positive charge, with negatively charged electrons scattered through it, like plums in a soft dough. In a model like that, there was nothing dense or concentrated enough anywhere inside the atom to seriously deflect a fast-moving particle passing through. The particles should sail straight through, maybe nudged slightly off course, but nothing more dramatic than that. But a small number of the particles, roughly 1 in 8,000, did something Thomson's model could not explain at all. They bounced back sharply. Some of them came almost directly back toward where they had come from, as though they had struck something small and unimaginably dense hidden deep inside the atom. This unexpected result genuinely stunned Rutherford. He later said, "It was almost as unbelievable as firing a large artillery shell at a piece of tissue paper and having it bounce back and hit you." The sheer improbability of those ricochets told him something important. Most of the atom was empty space, vast stretches of nothing, but buried at the very center was a tiny, extremely dense, positively charged core. Rutherford named this core the nucleus. To grasp the scale here, imagine a single grain of rice sitting in the middle of a large sports stadium. The grain of rice is the nucleus. The stadium around it, all that empty air and distant seating, is the rest of the atom, the space through which the much lighter, negatively charged electrons move. Almost all of the atom's actual mass is concentrated inside that grain of rice. Everything else is just the electrons, drifting through the empty stadium, so light that they barely register on the scale, compared to the dense core at the center. This was a complete reimagining of what matter actually looks like at its smallest scale. The solid world, the floor beneath you, the walls around you, the bones inside your own body, all of it is mostly empty space, held together by forces acting across that emptiness. This raised an obvious new question. What actually determined which element an atom belonged to, if it wasn't simply its overall weight? After all, Rutherford had shown that the nucleus carried a positive charge, and that different elements had nuclei with different amounts of charge. But the relationship between that charge and the chemical identity of the element was not yet clear. The answer came from a young English physicist named Henry Moseley in 1913, in work that was tragically cut short only 2 years later when he was killed in the First World War at the age of just 27. Moseley studied the X-rays given off by different elements when they were bombarded with high-energy electrons. He found something precise and beautiful. Each element gave off X-rays at a specific, characteristic frequency, and when he calculated backward from those frequencies, he found a number that increased in perfectly regular, whole number steps from one element to the next, with absolutely no exceptions and no fractional values in between. This number, he realized, represented the number of positively charged particles sitting in the nucleus of each atom. These particles had by then been given a name. They were called protons. Moseley called this number the atomic number, and it turned out to be the true underlying organizing principle that Mendeleev's original table by weight had only approximated. When elements were reordered by atomic number instead of atomic weight, every single one of the awkward exceptions in Mendeleev's original table resolved itself. The handful of elements Mendeleev had swapped out of strict weight order to preserve their chemical grouping fell into exactly the positions atomic number predicted they should occupy. Chemistry finally had its true underlying variable, not how heavy an atom happened to be, which could vary for reasons that had nothing to do with chemical identity, but how many protons sat at its very center, a number that turned out to define an element completely and absolutely. I want you to sit with that idea for a moment, because it's the true foundation everything else tonight is built on. Every atom of a given element, anywhere in the universe, on Earth or inside a star 1,000 light-years away, has exactly the same number of protons in its nucleus. That number, and nothing else, is what makes it that element. Change the number of protons, even by one, and you have created, in the truest possible sense, a completely different substance, with completely different properties. Gold has exactly 79 protons, not 78, not 80. 79. Always, everywhere, in every gold atom that has ever existed or ever will. The gold in a ring on your finger and the gold in a distant asteroid drifting through some other solar system are the same thing in the only way that fundamentally matters, because they share that same number of protons at the core. That fixed, unchanging number is the real anchor beneath the entire periodic table, the thing that gives it its structure, and it took chemistry more than 2,000 years, from Empedocles' four roots to Moseley's X-ray tubes, to find it. 2 millennia of wondering, guessing, measuring, and refining, all to arrive at a single whole number, different for each element, constant across the entire universe. If you're still with me, let your eyes close now if they aren't already. You don't need to follow every word from here. Just let it wash over you, slow and warm, the way a story sounds when you're already half asleep. The explanation continues either way, and there's nowhere you need to keep up with it. Just rest, and let the ideas settle in on their own. Now that we understand what an atomic number actually is, we can start to understand why the periodic table has the particular shape it has, the rows and columns you might remember from a classroom wall, and why elements sitting in the same column tend to behave so much alike. To understand that, we need to go a little deeper into the atom itself, into the electrons that surround that tiny, dense nucleus Rutherford found. In the early 1900s, a Danish physicist named Niels Bohr proposed a model of the atom that, while later refined by quantum mechanics, gave chemists an intuitive picture that still helps today. Bohr suggested that electrons do not simply swarm randomly around the nucleus. Instead, they occupy specific, defined energy levels. These levels are sometimes visualized as concentric shells, a bit like the layers of an onion, or the orbits of planets around a sun. The comparison to planets is only a rough starting picture, and we will refine it as we go. But for now, it is a useful way to hold the idea in your mind. Electrons in the shell closest to the nucleus have the lowest energy. They are held most tightly, tucked in near the dense positive core. Electrons in shells further out have higher energy. They are less tightly bound, more free to interact with the outside world. And crucially, each shell can only hold a specific maximum number of electrons before it is considered full. The innermost shell can hold at most 2 electrons. The next shell out can hold at most 8. The pattern continues outward, with more complex rules applying to shells further from the nucleus, which we will get to shortly. But the key point for now is simply this. Shells fill in order, and once a shell reaches its limit, any additional electrons must go into a new shell further out. Here is where the real elegance of the periodic table comes into view. An atom's chemical behavior, The way it reacts with other atoms, the way it bonds, the way it forms compounds, is determined almost entirely by the electrons in its outermost shell, the ones furthest from the nucleus and most exposed to the outside world. Chemists call these outermost electrons the valence electrons. They are, in a real sense, the part of the atom that actually does the chemistry. The protons and the inner electrons matter enormously for defining what element an atom is, for giving it its name and its place on the table. But it is the valence electrons, sitting exposed on the outer edge, that determine how that atom will behave when it meets other atoms. The inner electrons are like the foundation of a house, essential but hidden. The valence electrons are the doors and windows, the parts that actually interact with everything outside. This is the key that explains why the periodic table is arranged the way it is. When Moseley's atomic number ordering is combined with this shell structure, something beautiful happens naturally. As you move along a row of the table, adding one proton and one electron at a time, you are, for most of that row, simply adding electrons into the same outer shell, one after another. You are filling up the same set of seats in that outermost room. But once that outer shell becomes completely full, the next electron has nowhere left to go, except into a brand new shell, further out. And at that point, the pattern essentially resets itself, beginning to fill up a new outer shell, one seat at a time, in a way that echoes how the previous row began. This is why the table has rows, which chemists call periods. A new row begins exactly when a new electron shell begins, and it is why elements sitting in the same column, which chemists call groups, share such similar chemistry. Every element in a given column has the same number of valence electrons in its outer shell, even though the elements themselves sit in entirely different rows, with entirely different total numbers of electrons and completely different overall sizes. Sodium and potassium, sitting in the same column, both have exactly one valence electron sitting alone in their outermost shell. That is why both metals react in such a strikingly similar and strikingly dramatic way when dropped into water. Both are willing to give up that single outer electron almost instantly to whatever else is nearby. The total number of electrons is different, the size of the atom is different, but the number of valence electrons is exactly the same, and in chemistry, that is what matters most. Let's slow down here and really absorb this idea, because it is worth repeating in a different way. Picture the outer shell of an atom as a room with a certain fixed number of chairs. Some atoms walk into that room with the chairs almost entirely empty, just one or two electrons scattered inside a very roomy space. Those atoms tend to be eager to give those electrons away, to become more stable by leaving the room emptier still, essentially finishing with a full shell just underneath instead. They find stability not by filling the room, but by emptying it entirely and relying on the full room one level below. Other atoms walk into the room with the chairs almost completely full, just one or two seats left. Those atoms tend to be eager to grab an electron from somewhere else, to fill the last seats and complete the room. They find stability not by emptying, but by finishing, by putting someone in every available chair. And some atoms find the room already perfectly, completely full, every seat occupied. Those atoms tend to want nothing at all. They are content and unreactive exactly as they are. This single idea, chairs in a room, some empty, some full, some in between, explains an enormous amount of chemical behavior across the entire periodic table. It is a simple picture, but it holds up remarkably well, and it is worth keeping in the back of your mind as we move through the rest of the table together. The elements that walk into the room with just one or two lonely electrons in an otherwise empty outer shell sit on the far left side of the table. These are the alkali metals in the very first column: lithium, sodium, potassium, rubidium, cesium, and francium. Each has a single valence electron, and each one, as a result, is dangerously reactive, willing to give that single electron away almost immediately to nearly anything they touch. Pure sodium metal, dropped into water, does not just dissolve quietly. It reacts violently, fizzing and racing across the surface, sometimes even catching fire, as it desperately gives up that one lonely electron to the surrounding water molecules. It is not being dramatic. It is simply following the logic of its own outer shell, seeking the stability that comes from losing that single, exposed electron. Right next to the alkali metals sits the second column, the alkaline earth metals. Beryllium, magnesium, calcium, strontium, barium, and radium. These each have two valence electrons instead of one. They are still quite reactive, still eager to give those electrons away, but somewhat less dramatically so than their neighbors one column over. Giving away two electrons is a bigger commitment than giving away one, and that slightly higher threshold makes these metals a little more restrained in their chemistry, though still far from calm. On the complete opposite side of the table, in the very last column before we reach a special group we will discuss in a moment, sit the halogens: fluorine, chlorine, bromine, iodine, and astatine. These elements walk into that outer shell room with the chairs almost entirely full, just one single seat left empty. As a result, halogens are desperately eager to grab a single electron from somewhere else to complete that last seat. This makes them, in their own way, just as reactive and dangerous as the alkali metals, though through the opposite mechanism. The alkali metals achieve stability by giving. The halogens achieve stability by grabbing. Chlorine gas is genuinely hazardous to breathe, precisely because of this hunger for one more electron, an eagerness so strong it will happily rip an electron away from the delicate tissue lining your lungs if given the chance. It is not malicious, it is simply following the same logic of the chairs, trying to fill that one empty seat by whatever means are available. And then, in the very last column of the table, sit the noble gases: helium, neon, argon, krypton, xenon, and radon. These elements walk into the room and find every single seat already occupied, a perfectly full outer shell, needing nothing from anyone else. As a result, noble gases are famously, almost stubbornly unreactive. They are content to drift alone rather than bond with other atoms. This is exactly why helium can be sealed inside a balloon for months without reacting with the rubber or the air around it, and why neon can be sealed inside a glowing tube for years, doing nothing but glowing, never combining with anything at all. They are complete in themselves, and that completeness makes them chemically silent. Between the alkali metals on the far left and the halogens and noble gases on the far right sits a wide, complicated middle section of the table. This is occupied by what chemists call the transition metals: iron, copper, gold, silver, nickel, zinc, and dozens more. These elements are more complex than the simple picture we have built so far, because their outer electron behavior involves not just the outermost shell, but a slightly more intricate arrangement involving shells that sit just underneath the surface as well. We will come back to exactly why that happens in a little while, when we look more closely at the actual mechanics behind shell filling. For now, it is enough to notice that the transition metals, as a group, tend to be sturdy, dense, often shiny, and capable of forming a wide range of different compounds. Some of them, like iron and copper, are essential to human life and to civilization more broadly. Others, like gold and platinum, have been prized for centuries precisely because of how reluctant they are to react with the air or water around them. Gold jewelry buried for thousands of years can be dug up still gleaming, essentially unchanged, because gold's outer electrons are arranged in a way that makes it deeply unwilling to bond with oxygen or moisture. It sits in that wide middle block, stable and unreactive, in a way that has made it valuable to humans for as long as we have been digging things out of the ground. Let's slow down and add one more layer to this room, with Chair's picture, because it explains something you have probably noticed in ordinary life without ever quite connecting it to atoms. When an atom on the far left of the table, eager to give away its one lonely electron, meets an atom on the far right, eager to grab one more electron to complete its shell, something very clean happens. The alkali metal simply hands its electron over to the halogen, The alkali metal, having given up an electron, is left with one more proton than electron, giving it an overall positive charge. The halogen, having gained an electron, is left with one more electron than proton, giving it an overall negative charge. Opposite charges attract, and the two atoms, now called ions rather than neutral atoms, snap together and hold on tightly. Chemists call this an ionic bond. This is exactly what happens when sodium meets chlorine, forming sodium chloride, which is simply ordinary table salt, sitting in a shaker on countless kitchen counters. The direct, everyday result of one atom's need to give an electron away, meeting another atom's equally strong need to receive one. Not every pairing of atoms is quite so lopsided, though. When two atoms have a more similar, more evenly matched hunger for electrons, rather than one giving and one taking outright, they can instead agree to share a pair of electrons between them. Both atoms' outer shells benefit from that shared pair at once, a bit like two people each keeping one hand on a single object between them, both technically holding onto it. Chemists call this a covalent bond. It is the kind of bond holding together the oxygen you breathe, two oxygen atoms sharing electrons between them, and the water filling your cells, oxygen sharing electrons with two separate hydrogen atoms, and nearly every molecule that makes up the soft, living tissue of your body. Carbon in particular is extraordinarily good at forming these shared, covalent bonds, not just with other elements but with more atoms of carbon itself, chain after chain and ring after ring. This is exactly why carbon sits at the center of every known form of life, capable of building the long, complex, branching molecules that biology depends on, in a way no other element on the table can quite match. There is a third kind of bond worth knowing about too, one that explains why metals behave the way they do, why they conduct electricity, why they can be hammered into thin sheets or drawn into wire without shattering. In a solid piece of metal, the outer valence electrons do not stay tied to any one particular atom at all. Instead, they become delocalized, drifting freely through the entire structure, shared loosely among every atom in the metal all at once. It is a bit like a shared pool of water flowing freely between many connected buckets, rather than sitting locked inside any single one. This is sometimes called the sea of electrons model, and it explains a great deal about metallic behavior at once. Because those electrons are free to drift, they can carry electrical current easily, which is why metals conduct electricity so well. Because the positively charged metal atoms are held together loosely by this shared electron sea, rather than by rigid, fixed bonds pointing in specific directions, metals can be bent and reshaped, hammered into thin foil, or stretched into long wire, without breaking apart the way a more rigidly bonded material would. The sea of electrons holds everything together, but it holds things loosely enough to allow movement and flexibility, a combination of properties that has made metals central to human technology for thousands of years. Now let's turn to the wider families of elements sitting within the main body of the table and look more closely at a few of them, since we have only introduced them briefly so far. Consider the lanthanides and actinides, those two long rows usually printed beneath the main body of the table. If you have ever looked at a periodic table and wondered why those two rows are separated out, placed below everything else like a footnote, there is a reason, and it connects back to the filling of those complex f orbitals we touched on a moment ago. The lanthanides, sometimes informally called the rare earth elements, are actually not especially rare in the Earth's crust in absolute terms. Some of them are more abundant than lead or silver, but they tend to be spread thin and mixed together in ways that make them genuinely difficult and expensive to separate and purify. They occur together in the same minerals, and because their chemical behavior is so similar, pulling them apart from one another is a slow, painstaking process. And yet, despite that difficulty, they have become quietly essential to modern technology. Neodymium, one of the lanthanides, is used to make some of the strongest permanent magnets that exist. These magnets are found inside the tiny motors of hard drives, the speakers of headphones, and the enormous turbines of wind farms. Without neodymium, many of the compact, powerful motors we rely on every day would be much larger, much weaker, or both. Europium and terbium, two more lanthanides, are used to produce some of the vivid red and green colors in television and phone screens. The screen you may have looked at earlier tonight, before you closed your eyes, relies on these quiet, unfamiliar elements to produce the colors you see. They are not famous. Most people have never heard of them, but they are woven into the fabric of daily life in ways that would be very difficult to replace. The actinides, sitting in the row below the lanthanides, include uranium and thorium, both naturally radioactive, both capable of sustaining the kind of nuclear chain reaction used in nuclear power plants. The same property that makes them useful for generating electricity, the slow, steady release of energy from their nuclei, also makes them capable, in different configurations, of sustaining the far more destructive chain reaction used in nuclear weapons. This is a sobering reminder, if one were needed, that the same physical properties making an element useful can, depending entirely on how humans choose to use them, become something far more dangerous. The element itself does not change. Its nature is fixed by its atomic number, by the count of protons in its nucleus. What changes is the use to which human hands put that nature. By now you may have drifted in and out a few times. That is exactly right. There is nothing to catch up on. Everything has been settling quietly, whether you were following closely or not. The same way rain settles into soil, whether or not anyone happens to be watching it fall. You can keep drifting. The next part will still make sense whenever you catch pieces of it. Let's go a little deeper now into the actual mechanics of how these electron shells fill, because there is a beautiful, almost musical logic underneath it, one that chemists spent decades working out. Remember that Bohr's original picture, tidy concentric shells like the layers of an onion, was a useful starting simplification, but the real picture, developed through quantum mechanics in the 1920s, is a little stranger and a little more precise. Instead of electrons occupying simple circular orbits, they actually occupy what physicists call orbitals, regions of space around the nucleus where an electron is likely to be found. These regions are shaped not like tidy circles, but like clouds, spheres, dumbbells, and more complex forms, depending on which type of orbital we are talking about. There are four basic types of these orbitals, given the letters S, P, D, and F. These names trace back, somewhat accidentally, to old spectroscopy terminology, describing the lines these elements produced when their light was split apart and studied. The letters originally stood for sharp, principal, diffuse, and fundamental, descriptions of how the spectral lines looked to the scientists observing them. The names stuck, even though they no longer carry any descriptive meaning. They are simply labels now, but they are labels that map directly onto the shape of the table. An s orbital is shaped roughly like a sphere, a single round cloud of probability surrounding the nucleus. Each s orbital can hold up to 2 electrons. A p orbital is shaped more like a dumbbell, or a figure 8, with 2 lobes extending in opposite directions from the nucleus. There are 3 differently oriented p orbitals available at each energy level, pointing along 3 different axes in space. This means the full set of p orbitals can hold up to 6 electrons, 2 in each of the 3 orientations. A d orbital has an even more complex shape, something like a cloverleaf, and there are 5 different d orbitals available at each level, holding up to 10 electrons in total, and an f orbital, the most complex shape of all, has 7 different orientations available, holding up to 14 electrons. Here is where the real elegance shows up. Electrons fill these orbitals following a specific, predictable order, generally filling the lowest energy orbitals first, before moving to higher energy ones. Chemists call this the Aufbau principle, from a German word meaning to build up. It is the same idea as water filling a series of buckets from the lowest to the highest, never spilling into a higher bucket until the lower one is full. And when you map out the order in which these orbitals fill, something remarkable happens. That order exactly matches the shape of the periodic table as we know it today. The 2 columns on the far left of the table, the alkali metals and alkaline earth metals, correspond to elements filling an s orbital. The 6 columns on the far right, from the boron group through to the noble gases, correspond to elements filling a set of p orbitals. The wide middle block, the transition metals, corresponds to elements filling a set of d orbitals, and the 2 long rows usually placed beneath the main body of the table, the lanthanides and actinides, correspond to elements filling the even more complex f orbitals. This is genuinely one of the most satisfying ideas in all of chemistry. The periodic table is not an arbitrary grid that happens to organize elements conveniently. Its very shape, the width of each block, the number of columns in each section, directly mirrors the underlying quantum mechanical rules governing how electrons fill space around a nucleus. 2 columns on the left because s orbitals hold 2 electrons, 6 columns on the right because p orbitals hold 6 electrons combined, 10 columns in the middle because d orbitals hold 10 electrons combined, 14 elements in each of those long bottom rows because f orbitals hold 14 electrons combined. The table's shape is not decoration. It is not a choice someone made because it looked tidy. It is quantum mechanics, made visible, laid out flat enough to hang on a classroom wall. There is a small twist worth mentioning here, because it explains why the transition metals sometimes behave a bit unpredictably. The order in which orbitals fill by energy is not perfectly identical to the simple shell-by-shell picture Bohr originally proposed. In particular, a d orbital belonging to an inner shell often fills after the s orbital of the next shell out has already filled. This is a slightly counterintuitive detail. It arises because the energy levels of different orbital types overlap and interleave with each other as atoms get larger and more complex. The neat, simple ordering of shells starts to blur a little at the edges. This is why the transition metals occupying that d orbital block show up starting in what we would otherwise think of as the 4th row of the table, rather than appearing immediately after the 2nd row. And it is part of why transition metals often display more complicated, varied chemical behavior than the simple alkali metals and halogens we discussed earlier. They can sometimes lose different numbers of electrons depending on the specific reaction they are involved in. Iron, for example, can form more than one distinct type of compound. Iron that has lost 2 electrons behaving noticeably differently from iron that has lost 3. This flexibility, this ability to shift between different states, is part of what makes transition metals so useful in so many different chemical contexts, from the oxygen-carrying hemoglobin in your blood to the catalysts that drive industrial chemical reactions on enormous scales. Now let's widen our view a little and talk about the different branches and extensions of the periodic table, the parts that go beyond the simple picture of rows and columns we have built so far. One of the most important extensions involves something we have not discussed yet at all, which is the existence of isotopes. Remember that an element is defined strictly by its number of protons, its atomic number. That number is the fixed, unchanging identifier we talked about earlier. But the nucleus of an atom contains something else too, particles called neutrons, which carry no electrical charge at all, and which add mass to the nucleus without changing which element the atom belongs to. 2 atoms of the very same element, with the exact same number of protons, can have different numbers of neutrons. Chemists call these variations isotopes of that element. Carbon, for example, almost always exists with 6 protons and 6 neutrons, giving it the familiar name carbon-12, referring to its total mass of 12 particles in the nucleus. But a small fraction of natural carbon exists as carbon-14, still 6 protons, but with 8 neutrons instead of 6, giving it a slightly heavier nucleus. Because isotopes share the same number of protons, they behave almost identically in ordinary chemical reactions, since chemistry is governed by electrons, not neutrons. A carbon-14 atom will form the same bonds, fit into the same molecules, and participate in the same reactions as a carbon-12 atom. The extra neutrons in the nucleus make no difference to the electron cloud around it, but their different masses, and in some cases their different nuclear stability, make isotopes tremendously useful and important in other ways. Carbon-14, unlike ordinary carbon-12, is mildly radioactive, It decays slowly and predictably over thousands of years, transforming bit by bit into nitrogen. This property allows scientists to use it as a kind of natural clock, measuring the age of ancient organic material, from wooden artifacts to the bones of long-extinct animals, by measuring how much carbon-14 remains inside them. This technique, called radiocarbon dating, works because every living thing continuously exchanges carbon with its environment while it is alive, breathing it in, eating it, absorbing it, keeping a roughly steady ratio of carbon-14 to ordinary carbon-12 inside its body the entire time it is alive. The moment something dies, that exchange stops, and the carbon-14 already present begins decaying away at a fixed, known rate, without being replenished. By carefully measuring how much carbon-14 remains in an ancient sample of wood, cloth, or bone, and comparing it to the amount a living organism would have contained, scientists can calculate with reasonable precision how long ago that organism died. This technique has been used to date everything from ancient shipwrecks to the Dead Sea Scrolls to the remains of prehistoric humans. The quiet ticking of radioactive decay, built into the structure of certain isotopes, becomes a way of reaching backward through time. Isotopes matter in medicine too, in ways that touch an enormous number of people directly. A radioactive isotope of iodine is used both to diagnose and to treat certain thyroid conditions, because the thyroid gland naturally absorbs iodine from the bloodstream, regardless of which isotope it happens to be. The thyroid cannot tell the difference between ordinary, stable iodine and radioactive iodine. It takes up both, concentrating them in the same way. This allows doctors to either track the isotope's faint radioactive signal to see how the thyroid is functioning, or, at a higher dose, to use that same radioactivity to selectively destroy overactive thyroid tissue from the inside, while leaving the rest of the body largely untouched. The treatment is targeted, quiet, and precise, relying entirely on the fact that the thyroid reaches out and gathers iodine to itself, no matter what form that iodine takes. Isotopes of technetium, an element that barely exists in nature at all and is instead produced artificially, are used in a huge share of medical imaging scans performed around the world every single day. Technetium's particular radioactive properties make it detectable with imaging equipment, the cameras that let doctors see inside the body without making a single incision, while still decaying away quickly enough afterward to minimize the radiation dose a patient receives. Millions of people each year are injected with a tiny amount of technetium, just enough to light up on a scan, just enough to reveal the shape and function of a heart, a bone, an organ that needs examining. The technetium does its work, sends its signal, and then fades away, its radioactivity dropping to harmless levels within hours. Few of those patients ever learn the name of the element that made their diagnosis possible. It is simply there, doing its quiet work, and then it is gone. And isotopes even help explain something about your own past that has nothing to do with medicine or archaeology at all. The relative amounts of certain oxygen isotopes trapped inside your tooth enamel, laid down while you were still a child, quietly and permanently record something about the water you drank growing up. The ratio of heavier to lighter oxygen isotopes in rainwater varies depending on climate, altitude, and geography. Rain falling on a coastal plain carries a slightly different isotopic signature than rain falling high in the mountains. When you drink that water as a child, your body uses it to build the enamel of your teeth, and that enamel, once formed, does not remodel itself the way bone does. It stays fixed. It becomes a permanent record of the water you consumed during those early years. Forensic scientists and archaeologists have used exactly this kind of isotope analysis to determine where a person, sometimes centuries after their death, most likely spent their childhood, reading a kind of geographic fingerprint locked permanently into the mineral structure of their own teeth, without that person ever knowing, while they were alive, that their body was quietly keeping such a precise record. This idea of radioactive decay connects directly to another major extension of the periodic table, the elements sitting at the very far end of it, the ones with the highest atomic numbers. Every element up through atomic number 92, uranium, occurs naturally on Earth in meaningful quantities, though a small handful of elements below that number are so rare and so unstable that they exist naturally only in tiny, fleeting traces. But every element beyond uranium, atomic number 93 and higher, does not occur naturally on Earth at all, at least not in any lasting way. These are called the transuranium elements, meaning simply the elements beyond uranium. And every single one of them has been created artificially, inside laboratories, by physicists smashing smaller atomic nuclei together at tremendous speeds and hoping, against very difficult odds, that they fuse together into something new and heavier. The person most responsible for pioneering this work was an American chemist named Glenn Seaborg, working through the middle decades of the 1900s. Seaborg and his colleagues created a whole series of new elements this way: plutonium, americium, curium, berkelium, and more. These were elements that had never existed on Earth before human beings deliberately built them, atom by atom, inside particle accelerators. Think about that for a moment. For most of human history, the set of elements was fixed, given, a closed catalog of substances that had always been here. And then, in the 20th century, human beings began adding to that catalog, creating matter that the Earth had never seen, that the universe itself may never have produced in any lasting form anywhere else. Seaborg also proposed a significant restructuring of the periodic table itself. He argued that a group of elements previously scattered somewhat awkwardly within the main body of the table actually belonged together in their own distinct row beneath it, mirroring the lanthanides. This new row, the actinides, included uranium and all the transuranium elements Seaborg and his team were busy creating. In recognition of his enormous contribution, element 106 was eventually named Seaborgium, making Seaborg one of a very small number of scientists honored with an element named after them while they were still alive to see it. He could walk past a periodic table and see his own name printed there, in the box for element 106, a rare and fitting tribute to a life spent building the table itself. Creating these super-heavy elements only gets more difficult as the atomic numbers climb higher. The nuclei of these enormous atoms are so packed with protons, all positively charged and all repelling each other, that the strong nuclear force holding the nucleus together struggles more and more to keep everything from flying apart. Imagine trying to hold a handful of powerful magnets together, all facing the same direction, all pushing away from each other. Now imagine trying to add even more magnets to that handful, each one making the repulsion stronger. That is what it is like trying to build the heaviest elements. The repulsive force between all those protons is immense, and the nuclear force that binds them together only reaches across very short distances. As the nucleus grows larger, the balance between these two forces becomes more and more precarious. As a result, the heaviest elements on the periodic table today are extraordinarily unstable. They often exist for only a tiny fraction of a second before decaying into something else entirely. Element 118, Oganesson, named after the Russian physicist Yuri Oganessian, who led much of the research into super-heavy elements, has only ever been produced a handful of atoms at a time, in extraordinarily expensive, painstaking experiments. Each atom created has existed for less than a single millisecond before breaking apart. Less than 1,000th of a second, a flicker so brief that no human sense could ever register it directly. These atoms are born and die in a span of time too short for us to perceive, detectable only by the trails of energy they leave behind as they fall apart. And yet physicists keep pushing forward. They keep trying to synthesize elements even heavier still, driven partly by pure curiosity about where the table might end, and partly by a genuinely fascinating theoretical idea we will return to later tonight. It is the idea of a possible island of relative stability hiding somewhere out among these enormous, fleeting atoms, a region where the numbers of protons and neutrons might line up just right to produce something that lasts longer than a millisecond, something that might survive for minutes or hours or longer. Nobody has reached this island yet, but the possibility of it, the thought that somewhere out past the known edge of the table there might be stable ground, keeps drawing physicists back to their accelerators, keeps them building new experiments, keeps them searching. There is another major extension of the periodic table worth understanding, one that moves away from individual elements and toward the broader patterns, called periodic trends, that emerge when you look across the whole table at once. One of the clearest of these trends involves atomic size. As you move from left to right across a single row of the table, atoms generally get smaller, not larger, which can feel counterintuitive at first. After all, you are adding more protons and more electrons as you go. More particles should mean a bigger object, at least according to ordinary intuition. But atomic size does not work the way ordinary objects do. Remember that as you move across a row, those added electrons are going into the very same outer shell. They are not starting new shells. They are filling seats in the same room. Meanwhile, the number of protons in the nucleus is also climbing at the same time. More protons means a stronger positive pull from the nucleus. That stronger pull tugs the same outer shell of electrons in closer, tighter, resulting in a smaller overall atom, even though it technically contains more particles. The atom shrinks because the nucleus is pulling harder on the same cloud of electrons, drawing them inward. Moving down a column, on the other hand, atoms generally do get larger. Each row down adds an entirely new outer shell, further from the nucleus than the last. Even though the nuclear charge is also increasing as you go down, the effect of adding an entirely new shell, a new room built further out from the center, outweighs the increased pull. Physical distance simply grows with each new shell added, regardless of how strong the nuclear pull happens to be. The atom swells, layer by layer, as you move down through the rows. A closely related trend involves something called ionization energy, which is simply a measure of how much energy it takes to rip a single electron away from an atom entirely. Atoms with only one or two lonely valence electrons, like the alkali metals on the far left of the table, have very low ionization energies. They are already inclined to give that electron away, as we discussed earlier. It does not take much energy to persuade them to let go, because letting go is what they wanted to do anyway. Atoms with nearly full outer shells, like the halogens, have much higher ionization energies. They are clinging tightly to every electron they have, refusing to let any go without a genuine fight. Ripping an electron away from a halogen takes a great deal of energy, because that electron is exactly what the halogen needs to feel complete. And the noble gases, with their perfectly complete outer shells, have the highest ionization energies of all. They are extraordinarily reluctant to give up any electron at all, content and stable exactly as they are. Trying to pull an electron away from a noble gas is like trying to steal a seat from a room where every chair is already perfectly, comfortably occupied. There is no loose electron to grab, no weak point to exploit. The atom is closed, finished, complete, and it resists any effort to disturb that completeness. A third major trend, closely related to the first two, involves something chemists call electronegativity. This measures how strongly an atom pulls on electrons when it is bonded to another atom, essentially how much it wants to hoard shared electrons for itself within a chemical bond. Fluorine, sitting near the top right of the table, just one column over from the noble gases, has the highest electronegativity of any element. It pulls on electrons with an intense, almost greedy grip. This is part of why fluorine compounds tend to be so chemically stubborn and difficult to break apart once formed. Fluorine holds onto its electrons so tightly and pulls so strongly on any electrons nearby that the bonds it forms are unusually strong and unusually resistant to being broken. Elements on the far left of the table, by contrast, have very low electronegativity, since they are inclined to give electrons away rather than hoard them. They do not pull strongly on shared electrons because pulling is the opposite of what they want to do. They want to let go, to empty out, to find stability through loss rather than through gain. Taken together, these three trends, atomic size, ionization energy, and electronegativity, sweep across the table in smooth, predictable diagonal patterns. They generally increase as you move up and to the right. They generally decrease as you move down and to the left. These patterns are so reliable that a chemist, looking at any element's position on the table, can make confident, accurate predictions about how it will behave, often without ever having personally handled that element in a laboratory at all. The trends are built into the structure of the table itself, visible to anyone who knows how to read them. Now let's turn to where all of this actually lives, right now, tonight, in the world around you. It is easy, hearing about ancient Greek philosophers and quantum orbitals and particle accelerators, to feel like the periodic table is something distant, academic, locked away inside laboratories and textbooks. But it is not. It is woven into absolutely everything physically around you at this very moment, including your own body. Start with you. Roughly 65% of your body's mass, by weight, is oxygen, mostly bound up as water, filling your cells, cushioning your joints, carrying nutrients through your blood. About 18% is carbon, the backbone of every protein, every strand of your DNA, every cell membrane holding your body together. Carbon is an element so uniquely capable of forming complex, stable chains and rings with itself, that essentially all known life, everywhere, is built around it. Around 10% of your body is hydrogen, bonded everywhere alongside that oxygen and carbon. Roughly 3% is nitrogen, essential to every protein and to the DNA coiled inside nearly every one of your cells. And scattered through the rest, in smaller but still essential amounts, are calcium, giving structure to your bones and teeth. Phosphorus, working alongside that calcium and also forming the backbone of your DNA itself. Potassium and sodium, both alkali metals from that same reactive first column of the table, working together right now, at this very moment, to send the electrical signals racing along your nerves that let you feel the weight of the blanket over you. And iron, sitting quietly at the center of the hemoglobin in your red blood cells, gripping onto oxygen molecules and carrying them from your lungs to every distant corner of your body, including, right now, to the muscles gently rising and falling in your chest. The table is not somewhere else. It is not confined to a chart on a wall. It is inside you, right now, doing exactly what it has always done, whether you are thinking about it or not. The sodium and potassium in your nerves do not need you to understand them to keep firing. The iron in your blood does not need your attention to keep carrying oxygen. The calcium in your bones does not need your permission to keep holding you up. All of it is simply there, working quietly, following the same rules we have been tracing all evening, while you lie here in the dark and let the words wash over you. Look beyond your body, into the room around you, and the table is still there. The glass in your window is largely silicon, bonded with oxygen, arranged in the same fundamental structural pattern found in ordinary sand. Silicon and oxygen, linked together in a vast, repeating network, form the transparent pane that separates you from the night outside. It is the same material, at the atomic level, as the sand on a beach, simply heated and shaped until the atoms rearrange themselves into something clear and smooth and solid. If there is a phone charging somewhere nearby, its battery likely contains lithium, that same reactive alkali metal from the periodic table's leftmost column. Lithium is chosen precisely because its single, eager valence electron makes it exceptionally good at storing and releasing electrical charge efficiently. Each time you charge the phone and each time it drains again, lithium ions are shuttling back and forth inside that battery, giving up and taking back electrons. Over and over, a quiet, reversible chemical reaction that can repeat hundreds of times before the battery begins to lose its hold. The screen of that same phone likely contains indium, a soft, silvery metal combined with tin and oxygen, forming an unusual material that is simultaneously transparent to light and capable of conducting electricity. This allows your touch to be sensed right through the glass, your fingertip completing a circuit that tells the phone what to do. Indium is not an element most people think about. It sits in the middle of the table, one of those quiet transition metals, and yet without it, the touchscreen you may have used earlier tonight would not function. Wiring throughout your walls is almost certainly copper. Copper is chosen for how easily its outermost electrons move and flow, carrying electrical current efficiently across long distances with minimal loss. The sea of electrons inside a copper wire does not belong to any one atom. It drifts through the entire metal, a shared mobile cloud, ready to move the moment a voltage is applied. Copper has been used for this purpose for so long that it is easy to forget why it works so well. It works because its atomic structure, its particular arrangement of electrons in that d orbital block, makes it one of the best conductors among all the elements. It is not an accident of history that copper became the standard for electrical wiring. It is a direct consequence of its place on the periodic table. And if the room has any exposed metal at all, a doorknob, a lamp fixture, there is a reasonable chance some part of it involves chromium or nickel. These are transition metals often added to steel, specifically because they resist rust and corrosion so effectively, protecting the iron underneath. Iron alone, exposed to air and moisture, will gradually oxidize, turning reddish-brown and flaking away. But add a layer of chromium, and the chromium forms a thin, invisible, tightly bonded oxide coating on the surface. A barrier so thin you cannot see it, yet so effective that it seals the iron away from the air entirely. The iron never rusts because the chromium has already done the reacting for it, forming a stable shield that nothing else can penetrate. This is why stainless steel stays shiny, why it can sit in a kitchen or a bathroom for years without showing any sign of age. The chromium is working, quietly, at the atomic level, protecting everything beneath it. Think too about how you got ready for bed tonight, and the table is woven through even that. Toothpaste often contains a compound of fluorine, that highly electronegative halogen we discussed earlier, added specifically because fluoride compounds strengthen the outer layer of tooth enamel. Fluorine pulls so strongly on electrons that when it becomes part of the mineral structure of your teeth, it makes that structure more resistant to the acid produced by bacteria in your mouth. The acid still comes. The bacteria still try to dissolve the enamel. But the fluorine, with its intense grip on the surrounding atoms, makes the enamel harder to break apart. If you drink tap water in many parts of the world, a small, carefully controlled amount of that same fluorine has likely been added deliberately, for exactly the same reason. It is one of the more quietly successful public health interventions of the last century, a small adjustment to the chemistry of drinking water that has measurably reduced tooth decay across entire populations. Fluorine, the most electronegative element on the table, the one that grabs electrons more tightly than any other, ends up quietly protecting millions of smiles. If you swallowed a vitamin or a mineral supplement earlier today, there is a good chance it contained zinc, another transition metal, essential in small amounts for your immune system and for the healing of wounds. Or perhaps magnesium, sitting in that same reactive second column as calcium, playing a quiet supporting role in hundreds of different chemical reactions happening inside your cells at every moment. Magnesium is needed for the reactions that produce energy, for the signals that travel along nerves, for the very process that lets muscles relax, including, right now, the reactions that let your muscles relax enough for you to lie still and rest. The magnesium in your body is not aware of what it is doing. It is simply present, an ion floating in the fluid inside your cells, and when the right enzyme needs it, it is there, fitting into the right pocket of the right protein, allowing the chemistry of relaxation to proceed. Even the light in the room, if there is still a lamp glowing somewhere nearby, depends on the periodic table in a very literal, very physical way. An old-fashioned incandescent bulb glows because electricity forces its way through an extremely thin filament, traditionally made of tungsten. Tungsten is a transition metal chosen specifically because it has the highest melting point of any metal on the entire table. When electricity passes through that thin tungsten wire, the wire heats up and it glows, producing a warm, familiar light. The wire reaches temperatures that would melt almost any other metal into a puddle. But tungsten holds firm, glowing white-hot, without simply melting and breaking the circuit. It can do this because of the strength of the bonds between its atoms, a strength that is itself a consequence of tungsten's particular electron configuration, its place among the transition metals, its specific atomic number. A modern LED bulb works through an entirely different mechanism. It is built from carefully engineered layers of elements like gallium, arsenic, indium, and nitrogen, arranged so precisely that electrons moving through the material release their extra energy directly as light rather than as heat. This is a far more efficient process, and one that depends on decades of extremely precise chemistry. Engineers had to understand exactly how each of those elements' outer electrons behave, and how to layer different materials together so that electrons would jump across the boundary between them in just the right way to produce visible light. The precision required is measured in individual atoms, the layers only a few atoms thick in some cases. The soft glow of an LED bulb is a direct expression of quantum mechanics, the same rules that shape the periodic table, engineered into a device that sits quietly on a bedside table. And if you were to look up, past the ceiling, past the roof, into the night sky above wherever you are lying right now, the table continues out there too, at a scale that is almost difficult to hold in your mind. Every element heavier than hydrogen and helium, meaning essentially every element that makes up your body, your room, and the entire solid world around you, was originally forged inside the nuclear furnace of a star, through a process astronomers call nucleosynthesis. Stars spend most of their long lives fusing hydrogen into helium. Deep in their cores, under unimaginable pressure and temperature, hydrogen nuclei are forced together to form helium, releasing energy in the process. This is what makes a star shine. This is what makes our own sun shine, steadily, quietly, day after day. But as stars age and the hydrogen in their cores begins to run low, some of them go on to fuse helium into carbon, and carbon into oxygen, and continue building steadily heavier elements deep within their cores. Layer by layer, element by element, the star builds the materials that will one day become planets, become oceans, become living things. But elements heavier than iron cannot be created through this ordinary, gentle stellar fusion process. There is a reason for this. Fusing light elements together releases energy, which is why stars can keep burning. But iron sits at a special point on the periodic table. Its nucleus is so tightly bound that fusing anything heavier than iron actually consumes energy rather than releasing it. Instead of giving off energy to keep the star burning, the fusion of heavier elements would take energy away. This is the exact opposite of what keeps a star stable and shining. Once a star begins trying to fuse iron, it is in trouble. The energy that has been flowing outward, holding the star up against the crush of its own gravity, begins to falter. Instead, those heavier elements, everything from cobalt to gold to iodine to uranium, are created in vastly more violent, catastrophic events. They are forged in the explosive death of massive stars in supernovae, when a star that has run out of fuel collapses inward and then rebounds outward in an explosion so bright it can briefly outshine an entire galaxy. In that brief, unimaginably intense moment, the conditions are right for building the heaviest elements, the ones that ordinary stellar fusion can never produce. And, as astronomers have more recently confirmed, these heavy elements are also created in the incredibly energetic collisions of ultra-dense neutron stars smashing into one another, events so violent they ripple the fabric of space-time itself. The gold in a wedding ring, the iodine your thyroid gland needs to function properly, both were created in some of the most violent events the universe is capable of producing. They were scattered outward across space, drifting for billions of years as clouds of gas and dust, before eventually becoming part of the cloud that condensed to form our solar system. And eventually, almost impossibly specifically, some small fraction of that scattered stellar material became part of you. The iron in your blood was once inside a star that exploded. The calcium in your bones was once drifting through interstellar space. The oxygen you are breathing right now was fused in the core of a star that died long before the Earth was born. This is not poetry, it is not metaphor, it is a literal physical description of where the atoms in your body came from. Every atom heavier than hydrogen and helium has a history that passes through a star, and for the heavier elements, through a stellar explosion. You are, in the most straightforward physical sense, made of stardust, scattered across space and reassembled over billions of years into a living, breathing human being, lying here in the dark, listening to these words. The table we have been tracing tonight, the quiet grid of elements organized by atomic number, is not just a chart on a wall. It is a map of where you came from. It connects the calcium in your bones to a supernova that exploded somewhere in this galaxy long before the sun ignited. It connects the iron in your blood to a stellar core that collapsed and burst outward, seeding the cosmos with the materials that would one day become you. The periodic table is a family tree of matter, and every element on it, with the exception of the very lightest, was born in the heart of a star. That is the scale at which this story operates. Not the scale of a laboratory bench or a textbook page, but the scale of galaxies and supernovae and billions of years of cosmic time. And somehow, all of that vast and violent history fits into a single chart that can be printed on a piece of paper and hung on a classroom wall. Let's turn now to the harder questions, the parts of this story that remain genuinely open, debated, and in some cases strange, even to the scientists who study the periodic table professionally today. Even the shape of the table itself, the specific grid layout you have probably seen printed on classroom walls, is not the only way of drawing this pattern, and it is not universally agreed to be the best one. The standard rectangular table is a compromise, useful and familiar, but chemists and educators have proposed dozens of alternative layouts over the years. Some of these alternatives are spirals that wind outward from hydrogen at the center, emphasizing the continuous, unbroken nature of the pattern rather than the sharp breaks between rows. Others are three-dimensional structures that try to capture relationships the flat grid cannot show clearly, connections between elements that sit far apart on the standard table but share subtle chemical similarities that the rectangle obscures. Still others are circular forms that emphasize the cyclical, repeating nature of the pattern, the way the properties of elements return again and again as you move outward from the center, rather than presenting it as a simple left-to-right, top-to-bottom chart. None of these alternatives has replaced the standard table in everyday use, mostly because the rectangular version is now so deeply familiar that switching would cause more confusion than clarity. But their continued existence is a quiet reminder that the table's grid shape is a choice about how to represent an underlying pattern, not the pattern itself. The underlying pattern, the periodic law, the repeating rhythm of properties governed by atomic number, would remain exactly as true no matter which shape we chose to draw it in. The map is not the territory. The chart is not the thing itself. It is simply the best tool we have found so far for making a deep and complex pattern visible at a glance. There is an odd, almost playful debate, too, sitting right at the very top of the table, involving the two lightest elements of all. Hydrogen, with its single lonely electron, is almost always printed at the very top of the alkali metal column, grouped alongside lithium, sodium, and potassium. It is placed there simply because it shares their single valence electron, one electron in the outer shell, same as lithium, same as sodium. On paper, it looks like it belongs. But hydrogen does not actually behave much like a reactive metal at all, under ordinary conditions. It is a gas, not a solid. It is colorless and light, not dense and shiny. And its chemistry in many situations looks just as much, if not more, like the halogens on the opposite side of the table. Hydrogen can just as easily gain a single electron to complete a tiny, two-electron shell, as it can lose its one electron entirely. In that sense, it resembles fluorine or chlorine, both of which are desperate to gain a single electron to complete their own outer shells. Hydrogen is small enough, and its outer shell is close enough to the nucleus, that it can play both roles, giving like a metal or taking like a halogen, depending on the circumstances. Some periodic tables print hydrogen floating alone above the rest of the grid, unattached to any column, precisely because chemists have never fully agreed on which family it truly belongs with. It is the lightest element, the simplest element, the element that sits at the very beginning of everything, and yet even now, after more than a century of studying it, we cannot quite decide which box it fits into. There is something quietly appropriate about that. The simplest thing in the universe, a single proton with a single electron, and it still resists easy categorization. Helium presents a similar, quieter puzzle. It is almost universally placed at the very top of the noble gas column, which makes sense given how thoroughly unreactive it is. Helium is the most chemically inert element in existence. It does not bond with anything, under almost any conditions. In that respect, it is a perfect noble gas, even more stubbornly unreactive than neon or argon. But based purely on its electron configuration, helium has only 2 electrons total, filling that tiny innermost shell completely. Most other noble gases have 8 electrons in their outer shell. Helium's outer shell is also its inner shell, and it holds only 2. Because of this, some chemists argue that helium's true natural neighbor should actually be beryllium, sitting at the top of the alkaline earth metal column instead. Beryllium also has 2 outer electrons, though arranged quite differently. Both placements have real justifications behind them, and the disagreement, small as it seems, is a useful reminder that even the most basic, most memorized parts of the periodic table rest on judgment calls about which properties matter most. There is no single, perfectly objective rule with no room for interpretation at all. The table is a human construction, built to reflect a natural pattern, and like all human constructions, it involves choices. One of the most genuinely open questions involves those super-heavy, artificially created elements we discussed earlier, the ones existing for only a tiny fraction of a second before falling apart. Physicists have a theoretical prediction, not yet confirmed, called the island of stability. The idea, based on certain patterns in how protons and neutrons arrange themselves most stably within a nucleus, suggests that somewhere among these unimaginably heavy, currently unstable elements, there might exist a specific combination of protons and neutrons that produces a nucleus significantly more stable than its neighbors. To understand why this idea exists, you have to picture the nucleus the way physicists do. Protons and neutrons inside the nucleus are not just jumbled together randomly. They arrange themselves in shells of their own, layers within the nucleus that echo the electron shells we discussed earlier. Just as electrons are most stable when their outer shell is full, nuclei are most stable when their nuclear shells are full. These full shells correspond to what physicists call magic numbers, specific counts of protons or neutrons that produce a nucleus more tightly bound and less likely to fall apart than its neighbors. The island of stability is the idea that somewhere out among the super-heavy elements, there might be a nucleus whose proton count and neutron count both happen to land on these magic numbers at the same time. If such a nucleus could be created, it might be dramatically more stable than the elements around it. It might exist for minutes or hours, or even, in the most optimistic versions of the theory, far longer than that, rather than the fraction of a millisecond typical of the super-heavy elements created so far. It would be an island of relative calm in a sea of extreme instability, a place where the usual rules briefly relent and allow something heavy and complex to persist. Nobody has reached this predicted island yet. Every super-heavy element synthesized so far has been created with fewer neutrons than theory suggests the island would require, largely because of the practical difficulty of the fusion reactions used to create them. To make a nucleus with the right number of neutrons, you would need to smash together 2 nuclei that are both unusually rich in neutrons, and that is technically very difficult to do. The beams and targets used in these experiments tend to produce nuclei that are neutron-poor, not neutron-rich, and so every new element created so far has fallen short of the predicted island. But the possibility remains genuinely open, and physicists around the world continue building and refining new experiments specifically aimed at finally reaching it. New accelerator facilities are being designed, new combinations of beams and targets are being calculated, all in the hope of one day touching solid ground on that theoretical island. There is a related, deeper question too, one that sits right at the edge of current scientific understanding. Does the periodic table actually have an end at all? For a long time, many physicists assumed there had to be some absolute upper limit to how many protons a nucleus could hold before collapsing entirely. The repulsive force between all those positively charged protons would simply become too great for the strong nuclear force to overcome, and no nucleus, no matter how carefully constructed, could hold together even for an instant. Some theoretical estimates have suggested a rough boundary somewhere around atomic number 170. Though this number comes with enormous uncertainty, the physics becomes increasingly difficult to model accurately as atomic numbers grow that large. The equations that describe nuclear behavior are already complex for lighter elements. For elements with more than 100 protons, they become genuinely daunting, and the predictions they produce depend sensitively on assumptions that are difficult to test. And it is increasingly difficult to test these predictions experimentally at all, given how extraordinarily hard, expensive, and slow it already is to synthesize elements at even the currently known upper edge of the table. Whether the periodic table simply fades out into ever more fleeting fractions of a fraction of a second, each new element existing for less time than the last until the very concept of existence becomes meaningless, or whether there is a genuinely hard, absolute boundary out there, past which no nucleus, no matter how carefully constructed, could ever hold together at all, remains a real, open, actively studied question. It is not a settled fact. It is a genuine unknown, a place where the map still says, "Here be dragons," and the dragons in question are the fundamental forces of nature pushing against each other at the very limit of what matter can endure. There is also something quietly strange happening with the very heaviest elements already created, something that connects all the way back to the elegant, orderly quantum mechanical rules we discussed earlier tonight. Those rules, the ones that so beautifully explain the shape of the periodic table for lighter and moderately heavy elements, start to bend and blur once you reach elements heavy enough. In the largest atoms, the innermost electrons are moving incredibly fast. They are tugged so strongly by the enormous positive charge concentrated in such a massive nucleus that they begin approaching a meaningful fraction of the speed of light itself. And at those speeds, Einstein's theory of relativity starts to noticeably affect how those electrons behave. Physicists call this relativistic contraction. The innermost electrons moving at relativistic speeds actually become slightly heavier, and their orbitals contract, pulling closer to the nucleus than they otherwise would. This in turn affects the outer electrons, shifting their energies and changing the way the atom interacts with other atoms. This means some of the heaviest elements, ones like oganesson sitting at the very edge of what is currently known, may not actually behave the way their simple position on the periodic table would predict. Oganesson sits directly beneath radon in the noble gas column, and based purely on its position, you would expect it to behave as another inert, unreactive noble gas, content and complete with its outer shell full. But theoretical calculations suggest oganesson might actually be significantly more reactive than its position implies, precisely because relativistic effects distort its electron behavior away from the clean, orderly pattern that works so well for lighter elements. Its electrons may not arrange themselves in the neat, predictable way that its column would suggest. The quantum mechanical rules that shape the rest of the table begin to warp under the extreme conditions at the heavy edge. Since only a handful of individual oganesson atoms have ever been created, each surviving for less than a millisecond, nobody has actually been able to test this prediction directly in a laboratory yet. You cannot perform a chemical experiment on an atom that vanishes before you can even begin, which means, right now, tonight, this remains a genuinely unresolved question, sitting exactly at the boundary between quantum mechanics and relativity, two of the most successful theories in all of physics, bumping up against each other in a strange and not yet fully understood way. If you were to hold all of tonight in one single image, it would be this. Picture a single, quiet grid, laid flat, with a shape that is not arbitrary at all, but is instead a direct, visible map of the invisible rules governing how electrons arrange themselves around a nucleus. Picture that grid stretching from the lightest, simplest atom of all, a single proton with a single electron drifting around it, all the way out to the heaviest, most fleeting atoms human beings have ever managed to create, existing for less than the blink of an eye before falling apart again. Picture every element on that grid connected, quietly and precisely, by the same handful of underlying forces. The pull of a nucleus on its electrons, drawing them inward. The particular comfort an atom feels when its outer shell sits exactly full or exactly empty, and nothing in between. The rules of quantum mechanics that dictate how many seats are in each room, and what shapes those rooms take, and in what order they fill. And picture that grid, that same quiet, structured map, humming away right now, inside your own body, in the calcium of your bones, and the iron of your blood, and the oxygen moving softly in and out of your lungs. And also stretched out overhead, in the vast, slow furnaces of dying stars, scattering the heavier elements of that same grid outward across space, patiently, over billions of years, until some small portion of it eventually became you, lying here, tonight, breathing quietly in the dark. The same elements, governed by the same rules, forged in the same stellar explosions, now arranged into a living, thinking human being, resting under a blanket, listening to the sound of a voice describing the very atoms that make listening possible. That is really what the periodic table is. Not just a chart on a classroom wall, not just a list of names and numbers to memorize. It is a map of a pattern that was already there, humming quietly beneath the surface of everything, long before Empedocles ever looked at fire and water and wondered what they were made of, and long before Mendeleev ever left a gap in his table, trusting a pattern he could not fully explain yet. Human beings did not invent this pattern. We only, slowly, patiently, across more than 2,000 years, learned how to see it. Think back for a moment over the whole arc of what we have traced tonight. It began with a man on an island in the Mediterranean, watching the wind move through the trees and concluding that everything must be made of earth, water, air, and fire. It was a reasonable guess, given what he had to work with. He had his eyes, his reason, his attention to the world around him. He had no instruments, no way of looking closer than the surface of things, and yet he was asking the right question. What is everything made of, at the deepest level? That question never went away. It passed from Greece to the Islamic world, from alchemical workshops to the laboratories of Europe, from the precise scales of Lavoisier to the X-ray tubes of Moseley. Each generation added something, corrected something, refined the question and the methods for answering it. The four elements became 33, then 63, then 118 and counting. The philosophical speculations of Empedocles gave way to the careful measurements of Lavoisier. The secretive symbols of the alchemists gave way to the systematic predictions of Mendeleev. The solid, indivisible atoms of Dalton gave way to the mostly empty space of Rutherford. The neatly layered shells of Bohr, the probability clouds of quantum mechanics. Each layer of the story peeled back to reveal another layer beneath it, and each layer turned out to be governed by rules that are, at their core, mathematical and orderly and, in their own quiet way, beautiful. The periodic table as it stands today is not the end of that story. It is simply the current chapter. There are still questions we have not answered. The island of stability, if it exists, is still out there somewhere, waiting to be reached. The end of the table, if there is one, has not yet been found. The behavior of the heaviest elements, where relativity and quantum mechanics meet and blur, is still not fully understood. The table is not a finished document. It is a living map, and there are still blank spaces at the edges, places where future chemists and physicists will write their own discoveries, their own names, their own contributions to a story that began on a Greek island more than 2,000 years ago and is still being written tonight. And yet, for all its incompleteness at the edges, the core of the table is solid. The pattern is real. The atomic number, the count of protons, is the fixed and unchanging anchor. Gold is 79 protons, always and everywhere. Oxygen is 8. Carbon is 6. These numbers do not change, do not drift, do not depend on where you are or when you measure them. They are the same on Earth as they are in a galaxy a billion light-years away. They were the same when the first stars ignited as they are now, as they will be when the last stars burn out. That stability, that constancy, is what allows the table to serve as a map. The coordinates never shift, the landmarks stay in place. And those landmarks are not just abstract symbols, they are the literal substance of the world, and of you. The oxygen you are breathing, the iron in your blood, the calcium in your bones, the sodium and potassium quietly shuttling ions across the membranes of your nerve cells so that you can feel the texture of the blanket against your skin and hear the sound of these words. All of it is elements, all of it fits on the table, all of it was forged in stars. There is something quietly reassuring about that, I think. To know that the same rules that govern the distant galaxies govern the inside of your own body. To know that the iron carrying oxygen through your bloodstream was once inside a star that exploded, and that the explosion scattered that iron across space, and that eventually, after billions of years of drifting and coalescing, some of it found its way into you. You are not separate from the universe in the way it sometimes feels when you look up at the night sky. You are made of the same stuff, governed by the same laws, built from the same periodic table. The distance between you and the stars is not a distance of kind. It is only a distance of arrangement. The atoms in your body and the atoms in a star are the same atoms, obeying the same rules, just organized differently for a little while. And that brings us, gently, to the end of tonight. Somewhere in the dark room around you right now, atoms of oxygen and nitrogen are drifting quietly through the air, the same familiar mixture they have formed for as long as there has been anything alive on this planet to breathe them in. The ratio of oxygen to nitrogen in the atmosphere has been roughly stable for hundreds of millions of years, maintained by the breathing of plants and animals, the slow exchange of gases between the air and the oceans, the geological cycles that operate on timescales too vast for a single human life to perceive. You are breathing the same air, in terms of its basic composition, that your distant ancestors breathed, that the dinosaurs breathed, that the first creatures to crawl onto land breathed. The oxygen molecules moving in and out of your lungs right now have been breathed before, by countless living things, over countless generations. They have been part of the ocean, part of the soil, part of the atmosphere, cycling through the world in a slow, continuous dance that has been going on since long before there was anyone around to notice it. In your chest, iron is holding on to oxygen, carrying it patiently through you, the way it has every single night of your life, without you ever once having to think about it or ask it to. Each red blood cell contains millions of hemoglobin molecules, and each hemoglobin molecule contains 4 iron atoms, and each iron atom can grip a single oxygen molecule, holding it just tightly enough to carry it, just loosely enough to release it when it reaches a cell that needs it. This is not a process you control. It is not a process you need to supervise. It simply happens, continuously, reliably, every moment of every day and every night, whether you are awake or asleep, whether you are paying attention or not. The iron in your blood does not need your gratitude. It does not need your awareness. It just keeps working, quietly, steadily, the way it has since the moment you were born. In your bones, calcium sits arranged in a slow, sturdy lattice, holding you up, holding you together, quietly indifferent to whether you are awake or asleep. Calcium phosphate crystals, interspersed with collagen fibers, form a structure that is both strong and slightly flexible, capable of bearing weight and absorbing impact, capable of lasting a lifetime if cared for, capable of repairing itself when damaged. The calcium in your bones is the same calcium that forms chalk cliffs and marble statues and the shells of sea creatures. It is an alkaline earth metal, sitting in the second column of the periodic table. With 2 valence electrons it is happy to give away. In your bones it has given them away, bonding with phosphate and hydroxide to form a mineral called hydroxyapatite, which is, pound for pound, one of the strongest and most durable materials the natural world has ever produced. And it is inside you, right now, holding you up, keeping you whole. None of it needs your attention to keep working. None of it needs you to understand any of what we talked about tonight, in order to keep doing exactly what it has always done. The chemistry of you is not waiting for your permission. It is not waiting for your comprehension. It was already happening before you started listening, and it will keep happening, steadily, patiently, all through the rest of the night, whether you are following along or long since drifted off. So let it happen. Let the oxygen move in and out, slow and unhurried. You do not need to control your breathing. Your body knows how to breathe. It has been doing it since the moment you were born, and it will keep doing it all through the night, adjusting the rate and depth as needed, responding to the changing demands of your resting body without any conscious input from you. Just let the breath come and go at its own pace, in its own rhythm, the way the tide comes and goes, the way the seasons turn, the way the stars burn through their long, slow lives. Let the iron keep carrying it. The hemoglobin in your blood is doing its work right now, picking up oxygen in your lungs, carrying it through the branching network of your arteries and capillaries, delivering it to every cell that needs it, and then picking up the carbon dioxide those cells have produced, and carrying it back to your lungs to be exhaled. This is a journey that takes less than a minute from start to finish, and it repeats, over and over, thousands of times a day, millions of times over the course of a lifetime. The iron at the center of each hemoglobin molecule has been doing this work since before you were born, and it will continue doing it for as long as you live. It does not tire. It does not complain. It does not need to rest. It just keeps working, quietly, faithfully, the way iron atoms have been carrying oxygen in the blood of living things for hundreds of millions of years. Let the calcium keep holding you softly in place. The lattice of your bones is not rigid in the way a stone is rigid. It is alive, constantly being remodeled, constantly being broken down and rebuilt by the cells that live within it. Even now, as you lie still, osteoclasts are dissolving tiny amounts of bone, and osteoblasts are laying down new bone in its place. A slow, continuous cycle of renewal that replaces your entire skeleton roughly every 10 years. The calcium atoms in your bones today are not the same calcium atoms that were there a decade ago. They have been exchanged, replaced, cycled through your bloodstream and your diet, and back into your bones again. And yet the structure holds, the shape remains. The bones that are holding you up tonight are, at the molecular level, not the same bones you had when you were a child, and yet they are still yours, still doing the same job, still holding you together. There is nothing left to figure out tonight. No problem to solve, no puzzle to complete, no test to pass. The ideas we have talked about will still be here tomorrow, and the next night, and the night after that, if you ever want to come back to them. They are not going anywhere. The periodic table is not going anywhere. It will still be hanging on classroom walls, still be printed in textbooks, still be quietly organizing the elements of the universe, long after tonight has faded into memory. Just the quiet, steady chemistry of you, continuing on, exactly as it always has, while you rest. The sodium and potassium in your nerves, maintaining the electrical gradients that make thought and sensation possible. The carbon in your cells, forming the long chains and rings that make up your DNA, and your proteins, and every other molecule that keeps you alive. The oxygen in your lungs, diffusing across thin membranes into your bloodstream. The iron in your blood, gripping that oxygen and carrying it away. the calcium in your bones, standing silent guard over the soft tissues it protects, all of it working together, all of it following the same rules, all of it fitting into the same quiet grid that hangs on classroom walls around the world. All of it continuing, whether you are awake to notice it or not. So let yourself drift now, if you have not already. Let the words fade into the background, the way the stars fade when the sun comes up. Let the steady rhythm of your own breathing be the only sound you pay attention to, if you pay attention to anything at all. The periodic table will still be here when you wake. The atoms in your body will still be here, still doing their work, still following their rules, still carrying the history of the universe inside them. Nothing is lost by letting go. Nothing is wasted by falling asleep. The chemistry continues. The stars continue. The elements continue. And so do you, quietly, steadily, breathing in and out in the dark, a small, warm, living collection of stardust, arranged just so, for just this little while, in just this particular way. Rest now. The universe can manage without your attention for a few hours. It has been doing this for a very long time. It knows what it is doing. Let it carry you. And that brings us, gently, to the end of tonight. Somewhere in the dark room around you right now, atoms of oxygen and nitrogen are drifting quietly through the air. The same familiar mixture they have formed for as long as there has been anything alive on this planet to breathe them in. The ratio of oxygen to nitrogen in the atmosphere has been roughly stable for hundreds of millions of years, maintained by the slow, steady breathing of the living world. Plants take in carbon dioxide and release oxygen. Animals breathe in oxygen and release carbon dioxide. The oceans absorb and release gases in a rhythm tied to temperature and season and the life teeming within them. The whole system, vast and intricate, keeps the air you are breathing right now in a balance that has held, more or less, since long before the first human being ever opened their eyes and looked up at the sky. In your chest, iron is holding on to oxygen, carrying it patiently through you, the way it has every single night of your life, without you ever once having to think about it or ask it to. Each red blood cell is packed with hemoglobin, and each hemoglobin molecule is built around 4 iron atoms, and each iron atom can grip a single oxygen molecule with just the right strength. Strong enough to hold on for the journey from your lungs to the farthest reaches of your body, weak enough to let go when the oxygen is needed by a cell that has been working and waiting for it. This is not a process you direct. It is not a process you even notice most of the time. It simply happens, continuously, quietly, every moment of every day and every night, whether you are awake or asleep, whether you are paying attention or lost in dreams. In your bones, calcium sits arranged in a slow, sturdy lattice, holding you up, holding you together, quietly indifferent to whether you are awake or asleep. The mineral that gives your bones their strength is called hydroxyapatite, a compound of calcium, phosphorus, and oxygen, arranged in a crystalline structure that is both strong and just slightly flexible. Strong enough to bear your weight, to anchor your muscles, to protect the soft organs sheltered within your ribcage and your skull. Flexible enough to absorb the small shocks and stresses of daily life without shattering. And all of it, every atom of calcium in that lattice, is an alkaline earth metal from the second column of the periodic table, an element with 2 valence electrons it was eager to give away, now locked into a stable, solid form that will hold you up for as long as you live. None of it needs your attention to keep working. None of it needs you to understand any of what we talked about tonight in order to keep doing exactly what it has always done. The chemistry of you is not waiting for your comprehension. It is not waiting for your gratitude. It was already happening before you started listening. And it will keep happening, steadily, patiently, all through the rest of the night, whether you are following along or long since drifted off. So let it happen. Let the oxygen move in and out, slow and unhurried. You do not need to control your breathing. Your body knows how to breathe. It has known how to breathe since the moment you were born, since that very first sharp intake of air that filled your lungs and set everything in motion. It will keep knowing how to breathe all through the night, adjusting the rhythm as needed, slowing down as you sink deeper into rest, speeding up slightly if you shift or dream, always keeping the balance just right, without any conscious input from you. Just let the breath come and go at its own pace, in its own time, the way the tide comes and goes, the way the seasons turn, the way the stars burn through their long, slow lives. Let the iron keep carrying it. The hemoglobin in your blood is doing its work right now, picking up oxygen in the tiny air sacs of your lungs, carrying it through the branching network of your arteries and capillaries, delivering it to every cell that needs it. Your brain cells right now are using oxygen to process the sound of these words. Your heart cells are using oxygen to keep beating, steadily, reliably, as they have done since before you were born. Your muscle cells are using oxygen to stay gently relaxed, letting you sink into the mattress beneath you. And when each hemoglobin molecule has delivered its oxygen, it picks up carbon dioxide, the waste product of all that cellular work, and carries it back to your lungs to be exhaled. This cycle, this quiet, essential exchange, has been repeating in your body every few seconds for your entire life. It will continue all through tonight. It will continue tomorrow, and the next day, and all the days after that. The iron does not tire. It does not need to rest. It just keeps working, the way iron atoms have been carrying oxygen in the blood of living creatures for hundreds of millions of years. Let the calcium keep holding you softly in place. Your bones are not dead stone. They are living tissue, constantly being remodeled, constantly being broken down and rebuilt by the cells that live within them. Even now, as you lie still, tiny amounts of bone are being dissolved by cells called osteoclasts, and new bone is being laid down by cells called osteoblasts, a slow, continuous cycle of renewal that replaces your entire skeleton roughly every 10 years. The calcium atoms in your bones tonight are not the same calcium atoms that were there a decade ago. They have been exchanged, cycled through your bloodstream and your diet, absorbed from the food you ate and the water you drank, and then woven into the living fabric of your skeleton. And yet the structure holds. The shape remains. The bones that are holding you up tonight are, at the molecular level, not the same bones you had when you were a child, and yet they are still yours, still doing the same job, still holding you together with the same quiet, dependable strength. There is nothing left to figure out tonight, no problem to solve, no puzzle to complete, no test to pass. The ideas we have talked about will still be here tomorrow, and the next night, and the night after that, if you ever want to come back to them. They are not going anywhere. The periodic table is not going anywhere. It will still be hanging on classroom walls, still be printed in textbooks, still be quietly organizing the elements of the universe, long after tonight has faded into memory. Just the quiet, steady chemistry of you, continuing on, exactly as it always has, while you rest. The sodium and potassium in your nerves, maintaining the electrical gradients that make thought and sensation possible. Every thought you have ever had, every feeling you have ever felt, every memory you have ever stored, all of it depends on the movement of sodium and potassium ions across the membranes of your nerve cells. These two alkali metals, sitting right next to each other in the first column of the periodic table, are the reason you can think and feel and remember. They are the reason you can hear the sound of these words and understand what they mean. They are the reason you can lie here in the dark and let your mind drift, knowing that when you wake, everything you are will still be there, waiting for you. The carbon in your cells, forming the long chains and rings that make up your DNA, and your proteins, and every other molecule that keeps you alive. Carbon is unmatched in its ability to bond with itself, to form chains and rings and branching structures of almost infinite variety. It is the backbone of every organic molecule in your body, the scaffold on which all the chemistry of life is built. The carbon atoms in your DNA right now hold the instructions for building and maintaining every part of you. The carbon atoms in your proteins are doing the work of keeping you alive, catalyzing reactions, providing structure, sending signals. And all of that carbon was once inside a star, fused from helium in the slow, steady burning of a stellar core, before being scattered across space to become part of a planet, part of a biosphere, part of you. The oxygen in your lungs diffusing across thin membranes into your bloodstream. The distance between the air in your lungs and the blood in your capillaries is less than 1,000th of a millimeter, a barrier so thin it can barely be called a barrier at all. Oxygen slips across it effortlessly, moving from a place of higher concentration to a place of lower concentration, following the simple, physical logic of diffusion. It requires no energy, no effort, no attention. It just happens, the way water flows downhill, the way heat radiates from a warm body into a cool room. The oxygen wants to go where it is needed, and your lungs are built to let it. The iron in your blood, gripping that oxygen and carrying it away. The bond between iron and oxygen is just right, strong enough to hold, weak enough to release. If it were any stronger, the oxygen would never let go, and your cells would suffocate. If it were any weaker, the oxygen would slip away before reaching its destination, and your cells would starve. The bond is tuned to exactly the right strength, and it has been tuned that way for millions of years, since the first creatures evolved hemoglobin as a way to carry oxygen more efficiently than simple diffusion could manage. You are the inheritor of that long, slow process of refinement, and your blood right now is carrying oxygen with the same molecular machinery that has been carrying it in living things since long before anything resembling a human being existed. The calcium in your bones, standing silent guard over the soft tissues it protects. Your skeleton is a fortress, and calcium is its stone, but it is a living fortress, constantly repairing itself, constantly adapting to the stresses placed upon it. When you walk, when you run, when you lift something heavy, your bones respond by growing denser, stronger, more resistant to fracture. When you rest, when you lie still, your bones are not idle. They are maintaining themselves, replacing old material with new, checking for damage and repairing it. The calcium lattice that holds you up tonight is not a static structure. It is a dynamic, responsive, living tissue, and it has been keeping you safe and whole for your entire life. All of it working together, all of it following the same rules, all of it fitting into the same quiet grid that hangs on classroom walls around the world. The periodic table is not separate from you. It is not an abstraction, a piece of arcane knowledge locked away in textbooks and laboratories. It is the literal substance of your body, the literal substance of the air you breathe, the literal substance of the world around you, the same elements, governed by the same rules, arranged in the same patterns, are inside you and outside you, above you and below you, everywhere and always. All of it continuing, whether you are awake to notice it or not. The chemistry of life does not depend on your awareness. It does not require your permission. It is a self-sustaining, self-regulating system of extraordinary complexity and resilience, and it has been running for your entire life without any need for your conscious direction. Tonight, while you sleep, it will keep running. Your heart will keep beating. Your lungs will keep breathing. Your cells will keep repairing themselves, replacing worn-out parts, fighting off invaders, doing the quiet, invisible work of keeping you alive. You do not need to supervise any of it. You do not need to worry about any of it. You can simply let go, let the chemistry do what it has always done, and trust that when you wake, everything will still be there, still working, still holding you together. So let yourself drift now, if you have not already. Let the words fade into the background, the way the stars fade when the sun comes up. Let the steady rhythm of your own breathing be the only sound you pay attention to, if you pay attention to anything at all. The periodic table will still be here when you wake. The atoms in your body will still be here, still doing their work, still following their rules, still carrying the history of the universe inside them. Nothing is lost by letting go. Nothing is wasted by falling asleep. The chemistry continues. The stars continue, the elements continue, and so do you, quietly, steadily, breathing in and out in the dark, a small, warm, living collection of stardust, arranged just so, for just this little while, in just this particular way. Rest now. The universe can manage without your attention for a few hours. It has been doing this for a very long time. It knows what it is doing. Let it carry you. So let yourself drift now, if you have not already. Let the words fade into the background, the way the stars fade when the sun comes up. Let the steady rhythm of your own breathing be the only sound you pay attention to, if you pay attention to anything at all. The periodic table will still be here when you wake. The atoms in your body will still be here, still doing their work, still following their rules, still carrying the history of the universe inside them. Nothing is lost by letting go. Nothing is wasted by falling asleep. The chemistry continues. The stars continue. The elements continue. And so do you, quietly, steadily, breathing in and out in the dark, a small, warm, living collection of stardust, arranged just so, for just this little while, in just this particular way. Rest now. The universe can manage without your attention for a few hours. It has been doing this for a very long time. It knows what it is doing. Let it carry you. Think for a moment about what that means, to be carried by the universe. It is not a metaphor, not really. The same forces that hold galaxies together are holding you together right now. The same gravity that keeps the Earth in orbit around the Sun is pressing you gently into the mattress beneath you. The same electromagnetic force that powers the stars is firing the neurons in your brain, allowing you to hear these words, allowing you to understand them, allowing you to let them drift away as sleep comes closer. You are not separate from the universe, observing it from the outside. You are a part of it, made of it, sustained by it, and when you sleep, you are simply returning to a quieter state of that same existence, a state in which the chemistry continues, but the conscious mind steps back and lets it happen. The atoms in your body have been here for a very long time. They have been part of stars and oceans and mountains and countless other living things. They have been arranged and rearranged, combined and separated, cycled through the great systems of the earth, over and over again. For this brief moment, this single human lifetime, they are arranged as you. They are holding your shape, carrying your memories, sustaining your thoughts and feelings and dreams. And when you sleep, they do not stop. They keep working, keep renewing, keep maintaining the delicate, intricate pattern that is a living human being. That pattern is remarkably resilient. It can withstand injury and illness, stress and exhaustion, the wear and tear of daily life. It can repair itself, adapt itself, learn and grow and change. And yet it is also remarkably delicate. It depends on 1,000 small balances being maintained, 1,000 chemical reactions happening at the right rate and in the right order, 1,000 different elements from the periodic table being present in exactly the right amounts. Too much or too little of any one of them, and the pattern begins to fray. The fact that it works at all, that it has worked for your entire life without any conscious direction from you, is something worth pausing to appreciate. Not with effort, not with analysis, just with a quiet sense of recognition. Your body knows what it is doing. It has known since before you were born. You can trust it. Let your attention settle, if it has not already, on the simple fact of your own breathing, the air moving in, the air moving out, oxygen coming in, carbon dioxide going out, the iron in your blood carrying that oxygen to every part of you, the calcium in your bones holding you up, the sodium and potassium in your nerves. Quiet now, less active than when you are awake, but still maintaining their gradients, still ready to fire when needed. All of it happening without you, all of it continuing through the night. There is a kind of peace in that, I think, the peace of knowing that you do not have to hold everything together by yourself. You do not have to supervise your own heartbeat, or manage your own digestion, or direct your own immune system. Those tasks are being handled, competently and continuously, by systems that have been refined over millions of years of evolution, systems that are built into the very structure of your cells, into the very chemistry of your body. You can let go of the reins. You can close your eyes and let the machinery of life do what it does best, which is to keep living, keep functioning, keep maintaining the pattern that is you, even while the conscious part of you takes its rest. The night is a good time for this kind of letting go. The world outside is quiet. The demands of the day are behind you. The demands of tomorrow are still ahead, but they do not need your attention yet. Right now, in this moment, there is nothing you need to do, nothing you need to fix, nothing you need to worry about. There is only the darkness, the softness of the bed beneath you, the warmth of the blanket over you, and the slow, steady rhythm of your own breath. If thoughts come, let them come. If they go, let them go. You are not trying to force anything right now. You are not trying to achieve anything. You are simply allowing yourself to be, allowing the chemistry to continue, allowing sleep to come in its own time and in its own way. It will come. It always does. The body knows how to sleep, just as surely as it knows how to breathe. You do not need to make it happen. You only need to stop holding it back. And if you are still awake, still listening, still following the thread of these words, that is fine too. There is no deadline. There is no requirement. The words will continue for as long as you need them to, and they will be here tomorrow night and the night after that, if you ever want to come back to them. The periodic table is patient. The elements have been here for billions of years. They are in no hurry. Neither should you be. Let your breathing slow. Let your muscles relax. Start with your feet if you like, and notice any tension there, any holding on, and then let it go. Move up to your ankles, your calves, your knees. Let each part of you soften in turn, your thighs, your hips, your stomach. Let the tension drain away, your chest, your shoulders, your arms, your hands. Let them grow heavy and still. Your neck, your jaw, the muscles around your eyes. Let them release. You do not need to hold your face in any particular expression. You do not need to hold your body in any particular position. Just let yourself sink into the mattress, supported and held, the way the earth itself is held in its orbit, the way the stars are held in their galaxies, the way the atoms in your body are held in their quiet, orderly patterns. You are made of the same stuff as all of it. The iron in your blood and the iron in the core of a distant planet are the same element, governed by the same rules, forged in the same stellar explosions. The calcium in your bones and the calcium in a spiral galaxy a billion light-years away are the same element, with the same 20 protons, the same 2 valence electrons, the same place on the periodic table. The oxygen you are breathing and the oxygen being fused right now in the heart of some distant star are the same element, 8 protons, 8 electrons, the same familiar substance that makes up 1/5 of the air you breathe and 2/3 of the water in your body. You are not small. You are not insignificant. You are a part of something vast and ancient and ongoing, and you carry within you the history of the universe, written in the atoms that make up your bones and your blood and your breath. That history does not disappear when you sleep. It does not disappear when you wake. It is always there, always present, always true. The periodic table is not just a chart on a wall. It is a description of you, of everything you are made of everything you have ever touched or seen or breathed. It is a map of where you came from and a reminder of what you are a part of. So rest now in that knowledge. Rest in the knowledge that you belong here, that you are made of the right stuff, that the same forces that shaped the galaxies have shaped you too. Rest in the knowledge that you do not need to understand it all, that you do not need to hold it all in your mind, that it is enough simply to be a part of it, to be carried by it, to let it continue on while you close your eyes and let go. The night is deep and quiet. The world outside is still. The atoms in the air around you are drifting slowly, randomly, the way atoms have always drifted. The iron in your blood is carrying oxygen. The calcium in your bones is holding you up. The sodium and potassium in your nerves are maintaining their quiet, steady balance. Everything is as it should be. Everything is in its place. And you are here, in the middle of it all, a living, breathing part of the great pattern, a temporary arrangement of stardust, that has, for this brief moment, become aware of itself and of the stars it came from. Let that awareness soften now. Let it fade, the way the last light of sunset fades from the sky. You do not need to hold on to it. You do not need to remember it. It will still be true when you wake, whether you remember it or not. The periodic table does not depend on your memory. The elements do not need your attention. They were here long before you, and they will be here long after. And in the meantime, they will keep doing what they have always done, which is to make up the world and everything in it, including you, including this moment, including the quiet, steady sound of your own breathing in the dark. Sleep well. The universe has you. It has had you since the moment you were born, since the moment the first stars began to shine, since the moment the first atoms formed out of the cooling fire of the Big Bang. You are in good hands. You are made of good stuff. You can rest now. You can let go. The chemistry will continue. The stars will continue. And so will you, quietly, steadily, breathing in and out, a small, warm, living piece of the cosmos, at peace, at rest, at home. And that brings us, gently, to the end of tonight. Somewhere in the dark room around you right now, atoms of oxygen and nitrogen are drifting quietly through the air, the same familiar mixture they have formed for as long as there has been anything alive on this planet to breathe them in. In your chest, iron is holding onto oxygen, carrying it patiently through you, the way it has every single night of your life, without you ever once having to think about it or ask it to. In your bones, calcium sits arranged in a slow, sturdy lattice, holding you up, holding you together, quietly indifferent to whether you are awake or asleep. None of it needs your attention to keep working. None of it needs you to understand any of what we talked about tonight in order to keep doing exactly what it has always done. It was already happening before you started listening, and it will keep happening, steadily, patiently, all through the rest of the night, whether you are following along or long since drifted off. So let it happen. Let the oxygen move in and out, slow and unhurried. You do not need to control your breathing. Your body knows how to breathe. It has known since the moment you were born, and it will keep knowing all through the night, adjusting the rhythm as needed, slowing down as you sink deeper into rest. Just let the breath come and go at its own pace, in its own time, the way the tide comes and goes, the way the seasons turn, the way the stars burn through their long, slow lives. Let the iron keep carrying it. The hemoglobin in your blood is doing its work right now, picking up oxygen in your lungs, carrying it through the branching network of your arteries and capillaries, delivering it to every cell that needs it, then picking up the carbon dioxide those cells have produced and carrying it back to your lungs to be exhaled. This journey takes less than a minute from start to finish, and it repeats over and over, thousands of times a day, millions of times over the course of a lifetime. The iron at the center of each hemoglobin molecule has been doing this work since before you were born, and it will continue doing it for as long as you live. It does not tire, it does not need to rest. It just keeps working, quietly, faithfully, the way iron atoms have been carrying oxygen in the blood of living things for hundreds of millions of years. Let the calcium keep holding you softly in place. Your bones are not dead stone. They are living tissue, constantly being remodeled, constantly being broken down and rebuilt by the cells that live within them. Even now, as you lie still, tiny amounts of bone are being dissolved, and new bone is being laid down in its place. A slow, continuous cycle of renewal that replaces your entire skeleton roughly every 10 years. The calcium atoms in your bones tonight are not the same calcium atoms that were there a decade ago. They have been exchanged, cycled through your bloodstream and your diet, absorbed from the food you ate and the water you drank, and then woven into the living fabric of your skeleton. And yet the structure holds, the shape remains. The bones that are holding you up tonight are, at the molecular level, not the same bones you had when you were a child, and yet they are still yours, still doing the same job, still holding you together with the same quiet, dependable strength. There is nothing left to figure out tonight, no problem to solve, no puzzle to complete, no test to pass. The ideas we have talked about will still be here tomorrow, and the next night, and the night after that, if you ever want to come back to them. They are not going anywhere. The periodic table is not going anywhere. It will still be hanging on classroom walls, still be printed in textbooks, still be quietly organizing the elements of the universe, long after tonight has faded into memory. Just the quiet, steady chemistry of you, continuing on, exactly as it always has, while you rest. The sodium and potassium in your nerves, maintaining the electrical gradients that make thought and sensation possible. Every thought you have ever had, every feeling you have ever felt, every memory you have ever stored, all of it depends on the movement of these two alkali metals across the membranes of your nerve cells. They are the reason you can think and feel and remember. They are the reason you can hear the sound of these words and understand what they mean. They are the reason you can lie here in the dark and let your mind drift, knowing that when you wake, everything you are will still be there, waiting for you. The carbon in your cells, forming the long chains and rings that make up your DNA and your proteins and every other molecule that keeps you alive. Carbon is unmatched in its ability to bond with itself, to form chains and rings and branching structures of almost infinite variety. It is the backbone of every organic molecule in your body, the scaffold on which all the chemistry of life is built. The carbon atoms in your DNA right now hold the instructions for building and maintaining every part of you. The carbon atoms in your proteins are doing the work of keeping you alive, catalyzing reactions, providing structure, sending signals. And all of that carbon was once inside a star, fused from helium in the slow, steady burning of a stellar core, before being scattered across space to become part of a planet, part of a biosphere, part of you. The oxygen in your lungs, diffusing across thin membranes into your bloodstream. The barrier between the air in your lungs and the blood in your capillaries is less than 1,000th of a millimeter, a membrane so thin it can barely be called a barrier at all. Oxygen slips across it effortlessly, moving from a place of higher concentration to a place of lower concentration, following the simple, physical logic of diffusion. It requires no energy, no effort, no attention. It just happens, the way water flows downhill, the way heat radiates from a warm body into a cool room. The oxygen moves to where it is needed, and your lungs are built to let it. All of it working together, all of it following the same rules, all of it fitting into the same quiet grid that hangs on classroom walls around the world. The periodic table is not separate from you. It is not an abstraction, a piece of arcane knowledge locked away in textbooks and laboratories. It is the literal substance of your body, the literal substance of the air you breathe, the literal substance of the world around you, the same elements, governed by the same rules, arranged in the same patterns, are inside you and outside you, above you and below you, everywhere and always. All of it continuing whether you are awake to notice it or not. The chemistry of life does not depend on your awareness. It does not require your permission. It is a self-sustaining, self-regulating system of extraordinary complexity and resilience, and it has been running for your entire life without any need for your conscious direction. Tonight, while you sleep, it will keep running. Your heart will keep beating, your lungs will keep breathing, your cells will keep repairing themselves, replacing worn-out parts, fighting off invaders, doing the quiet, invisible work of keeping you alive. You do not need to supervise any of it. You do not need to worry about any of it. You can simply let go, let the chemistry do what it has always done, and trust that when you wake, everything will still be there, still working, still holding you together. So let yourself drift now, if you have not already. Let the words fade into the background, the way the stars fade when the sun comes up. Let the steady rhythm of your own breathing be the only sound you pay attention to, if you pay attention to anything at all. The periodic table will still be here when you wake. The atoms in your body will still be here, still doing their work, still following their rules, still carrying the history of the universe inside them. Nothing is lost by letting go. Nothing is wasted by falling asleep. The chemistry continues, the stars continue, the elements continue. And so do you, quietly, steadily, breathing in and out in the dark, a small, warm, living collection of stardust, arranged just so, for just this little while, in just this particular way. Rest now. The universe can manage without your attention for a few hours. It has been doing this for a very long time. It knows what it is doing. Let it carry you.